Hello there, and welcome to Science for Sleep, where curiosity gets comfortable, the lights grow a little dimmer, and even the most distant spacecraft are allowed to take the scenic route. Tonight, we're going to follow a signal that has been travelling farther than any human voice, photograph, radio broadcast, or mildly embarrassing message sent to the wrong group chat. It begins at a spacecraft called Voyager 1, a machine launched from Earth in 1977, when telephones still had cords, computers filled rooms, and nobody involved in the mission could have imagined that their spacecraft would still be answering us almost half a century later. Voyager 1 is now so far away that distance begins to lose its everyday meaning. You cannot picture it by imagining a long road, an ocean crossing, or even a journey to the moon. Those comparisons run out far too quickly. Voyager has passed every planet, crossed the outer boundary of the Sun's protective region, and continued into interstellar space, where the particles and magnetic fields around it are no longer dominated by the solar wind in quite the same way. It is still travelling outward, carrying a collection of scientific instruments, old computers, a large radio antenna, and a golden record containing sounds and images from Earth. More surprisingly, it is still in contact with the people who built it, or at least with the generations of engineers who inherited the responsibility of listening. So, before we begin, where are you listening from tonight? Perhaps you are somewhere surrounded by city lights, where radio signals from phones, routers, aircraft, and television towers move invisibly through the walls. Maybe you're in a quieter place, where the sky is dark enough to see a few planets and the broad mist of the Milky Way. And what time is it where you are? Whatever the answer, Voyager 1 exists in a very different relationship with time. A message sent from Earth cannot reach it during a short conversation, a meal, a workday, or even a full night's sleep. The spacecraft is so distant that a radio command takes more than 23 hours to cross the space between us. A reply requires the same journey in the opposite direction. Ask Voyager a question, and even if everything works perfectly, you must wait nearly 2 days to learn whether it heard you. That makes communication with Voyager less like a phone call and more like sending a letter across an ocean that has no ships, no islands, and no convenient tracking page telling you that your parcel is 8 stops away. Engineers transmit a command from Earth, watch it disappear at the speed of light, and then wait. There is no way to call it back. There is no way to correct a typing mistake halfway through the journey. By the time the instruction reaches Voyager, the people who sent it may have gone home, slept, returned to work, eaten lunch, and begun wondering whether they remembered to switch off the kitchen light. Then the spacecraft must receive the command, interpret it using computers designed in the 1970s, carry out the requested action, and send a response through a transmitter with less power than many household light bulbs. If you find this quiet journey through space soothing, interesting, or simply useful for keeping the more energetic parts of your mind occupied, while the rest of you settles down, I would be very grateful if you gave the video a like and perhaps subscribed. It helps this calm corner of science reach other listeners who may also enjoy falling asleep while thinking about machines that refuse to retire. Voyager 1 has certainly earned a long rest by now, although nobody appears to have told Voyager 1. Settle in, let the day become a little less urgent, and imagine for a moment that you're standing beside one of the giant antennas used to contact it. The dish is enormous, a curved metal surface wider than many buildings, mounted on machinery that allows it to turn with remarkable precision. It does not point toward a bright object that you could easily identify in the sky. Voyager is far too faint and far too distant to see. Instead, computers calculate where the spacecraft should be, allowing the antenna to aim at a tiny patch of darkness. Somewhere within that patch, billions of kilometers away, an object about the size of a small car is moving through interstellar space at tens of thousands of kilometers per hour. The dish waits for a signal. Nothing dramatic happens when it arrives. There is no glowing beam sweeping over the landscape. No deep voice announces that contact has been established. Voyager's transmission reaches Earth as an extraordinarily weak radio signal buried among natural noise, human-made interference, and the quiet electrical activity of the receiving equipment itself, the signal is so faint that the task of detecting it has often been compared to hearing a whisper from an impossible distance. Even that comparison may be too generous. A whisper travels through air and grows weaker as sound spreads. Voyager's radio transmission must cross more than 25 billion kilometers of space before the largest antennas on Earth attempt to distinguish it from the background. And yet, they do. This is the central puzzle of our journey. How can a spacecraft launched before modern laptops, smartphones, satellite navigation, and the World Wide Web still communicate from beyond the familiar neighbourhood of the planets? How can Earth aim a signal accurately enough to reach it? How does Voyager keep its antenna pointed back toward a planet that has become nothing more than a distant point near the Sun? What powers the transmitter when sunlight out there is far too weak for useful solar panels? How can engineers repair a computer they cannot touch, using instructions that take almost a day to arrive? And perhaps most surprisingly, how can an aging machine continue to understand commands created by people using technology that did not exist when it left Earth? Part of the answer is that Voyager 1 was built with extraordinary care. Another part is that the mission has benefited from decades of improvements made here on Earth. The spacecraft's hardware has not grown a larger antenna or received a new radio. Nobody has visited it to replace a circuit board, tighten a bolt, or blow dust out of a cooling vent. Voyager remains essentially the same physical machine that rose from Cape Canaveral on September 5, 1977. Earth, however, has changed around it. Receivers have become more sensitive. Signal processing methods have improved. Computers can identify patterns that earlier equipment might have missed. Several ground antennas can sometimes work together, combining their collecting power to hear a signal that would otherwise be too weak. Voyager therefore survives through a partnership between old machinery in space and constantly improving machinery on Earth. It is little like keeping contact with someone who owns the same telephone they used in 1977, while the entire telephone network around them has been rebuilt repeatedly. The caller has not upgraded, but the people listening have become much better at hearing. There is also the remarkable fact that Voyager does not need to send very much information at once. During its encounters with Jupiter and Saturn, the spacecraft transmitted photographs and large amounts of scientific data compared with what it sends today. Its current communications are much slower. At such distances, a high-speed connection would require far more transmitting power or a much larger antenna than Voyager possesses. Instead, information arrives patiently, bit by bit. A small amount of engineering data can reveal temperatures, electrical currents, voltages, instrument conditions, computer states, and the orientation of the spacecraft. Scientific measurements can be returned gradually, allowing researchers to study the thin material surrounding Voyager in interstellar space. You might think of the transmission as an extremely slow stream of carefully arranged yes or no answers. Digital information is built from bits, and each bit represents one of two states, usually described as a 1 or a 0. A photograph, a song, a bank record, and a message from Voyager can all be expressed using long sequences of these simple choices. Voyager does not need to explain its condition in sentences. It sends structured patterns, and computers on Earth translate those patterns into meaningful measurements. Of course, the weaker the signal becomes, the more difficult it is to decide whether a particular bit was a 1, a 0, or merely a burst of noise pretending to be useful. Engineers use error-correcting methods to protect the data. Extra information is included so that the receiving system can identify and repair certain mistakes caused during transmission. It is similar to repeating important details in a message, although the mathematical methods are far more efficient than simply writing, "Please remember the milk" 17 times. The spacecraft sends a coded signal, and the ground system checks the pattern for inconsistencies. Even when some parts are damaged or uncertain, the original information can often be reconstructed. The contact also depends on timing. Voyager's signal does not arrive whenever it feels like it. Earth's rotation carries each receiving station into and out of the correct position. NASA's Deep Space Network uses major antenna complexes located in California, Spain, and Australia. They are separated around the planet so that as Earth turns, distant spacecraft can remain within view of at least one region. When Voyager sinks below the horizon for one complex, another part of the network may be preparing to listen. Earth effectively passes the spacecraft from one group of antennas to the next, although Voyager itself is so distant that its position in the sky changes very slowly. This worldwide arrangement is necessary, because even a 70-meter dish cannot listen through the solid Earth. If Voyager is below the horizon, the planet itself is in the way, which is rather inconsiderate of the planet but difficult to correct. By spreading antenna sites roughly around the globe, the Deep Space Network gives mission controllers repeated opportunities to send commands and receive data. The same network also supports many other spacecraft, which means antenna time must be scheduled carefully. Mars orbiters, lunar missions, planetary probes, and distant observatories may all need attention. Voyager is important, but it is not the only spacecraft trying to call home. When an antenna transmits a command, radio energy is focused into a narrow beam, aimed toward the predicted location of Voyager 1. The beam still spreads as it travels. By the time it reaches the spacecraft, its energy has been diluted across an enormous area. Voyager's high-gain antenna, a white dish about 3.7 meters across, collects a tiny portion of that energy. The incoming signal is amplified and passed to the onboard electronics, where it is interpreted as a command. The spacecraft cannot simply point in approximately the right direction. Its antenna must remain aimed toward Earth with great care. Voyager has small thrusters that adjust its orientation. Sensors help it understand which way it is facing by referring to the Sun and certain stars. Periodically, the thrusters fire in brief pulses to keep the antenna aligned. If the dish turned too far away, the signal would weaken or disappear. Voyager could still be operating perfectly, but Earth would no longer hear it, rather like a person continuing a conversation after accidentally pointing the telephone at the sofa. These orientation systems have become one of the mission team's most delicate concerns. Thruster tubes can become clogged by residue from decades of use. Hardware originally intended for one purpose may need to be brought back into service for another. Engineers have revived equipment that had not been used for years and changed operating procedures to reduce strain. Every adjustment must be considered carefully, because Voyager has no repair crew, no spare parts delivery, and no helpful neighbour available to give the antenna a small push. Power is equally precious. Voyager is far beyond the distance where solar panels would be practical for a spacecraft of its design. Sunlight becomes weaker as you move away from the Sun, spreading across a larger area. At Voyager's location, the Sun is still the brightest star in its sky, but it provides only a tiny fraction of the energy received near Earth. The spacecraft instead relies on 3 radioisotope thermoelectric generators. These devices use heat produced by the natural decay of plutonium-238 and convert part of that heat into electricity. There is no miniature nuclear reactor running inside Voyager. No chain reaction is being controlled. The material simply releases heat as it decays, and thermocouples produce electric current from the temperature difference between hot and cooler parts of the generator. The system contains no turbines and no moving mechanical generator parts. That simplicity is one reason it can continue operating for so long. Unfortunately, the available power steadily declines. The radioactive material produces less heat as time passes, and the thermoelectric components also become less efficient. The spacecraft loses roughly 4 watts of electrical power each year. 4 watts may not sound serious. A modern household can waste more than that through devices left in standby mode. On Voyager, however, every watt matters. Mission engineers have spent years turning off heaters, instruments, and other systems to preserve enough electricity for essential operations. It is a careful process of deciding what can be sacrificed without causing another part of the spacecraft to become too cold unstable, or unusable. An instrument may consume power directly, but switching it off could also change the spacecraft's temperature. A heater may seem optional until a fuel line becomes cold enough to threaten the thrusters needed to point the antenna. Voyager's systems are connected in ways that make every saving a small engineering argument. As of 2026, Voyager 1 remains active, but its margins are narrow. NASA has continued switching off scientific instruments in a planned effort to extend the mission. The spacecraft can no longer operate everything it carried, and nobody expects that situation to improve. Each decision preserves power for the systems that remain. The goal is not to keep Voyager unchanged. That has not been possible for years. The goal is to allow it to continue returning at least some measurements from a region no other operating spacecraft has reached. This is what makes continued contact so valuable. Voyager 1 is not merely a distant souvenir. It is travelling through interstellar space and directly sampling particles, plasma, magnetic fields, and cosmic rays in its local environment. Telescopes can observe distant stars and clouds, but Voyager can measure the conditions around itself. Its data helps scientists study the boundary between the Sun's influence and the wider material of the galaxy. Even a slow trickle of information can be important because it comes from a place humanity has never examined in person by any other means. The spacecraft's age also creates problems that could not have been fully predicted in 1977. Electronic components have been exposed to radiation for decades. Memory can become corrupted. Temperature conditions change as heaters are switched off. Thrusters wear, sensors drift. A single incorrect value stored in the wrong place can disrupt the flow of data. In late 2023, Voyager 1 began sending information that mission controllers could not understand. The radio signal itself was still reaching Earth, which meant the spacecraft was alive and transmitting. But its science and engineering data had become unusable. That distinction matters. Losing meaningful data is not the same as losing the carrier signal. Imagine hearing someone speaking through a wall but discovering that they are repeating the same meaningless sound. You know the person is there. You know their voice is reaching you, but you cannot understand what they are trying to say. Engineers spent months investigating, sending commands and waiting almost 2 days for the outcome of each test. They eventually traced the problem to part of the flight data system's memory and found a way to move affected software instructions elsewhere. Voyager began returning usable engineering data again in April 2024, followed by science data from its operating instruments. Consider the patience required. A technician working on a computer in the same room can change a setting and see the result immediately. A Voyager engineer sends a command, waits more than 23 hours for it to arrive, then waits more than 23 hours for the response. If the test fails, the next attempt begins another 2-day cycle. A week may allow only a few meaningful exchanges. There is no rapid sequence of clicking buttons until something works. Every command must be checked, simulated, reviewed, and transmitted with the understanding that a careless instruction could make the situation worse. Voyager's computers have less memory and processing capability than devices we now treat as disposable. Yet raw computing speed is not the only measure of usefulness. These systems were designed for a narrow set of tasks. They do not need to stream films, load advertisements, update social media, or remind Voyager that several browser tabs are consuming energy. They monitor the spacecraft, manage commands, control instruments, maintain orientation, and prepare data for transmission. Their limited purpose makes them efficient, predictable, and understandable to the engineers who study them. Still, working with them requires knowledge that is becoming increasingly rare. Many of the original mission designers have retired, and some are no longer alive. Documentation written decades ago must be preserved and interpreted. New engineers learn systems created before they were born. Old software languages, hardware diagrams, test records, and handwritten notes can become essential when a fault appears. The mission is therefore not only a connection between Earth and a spacecraft. It is also a connection between generations of people. Someone designing Voyager in the 1970s had to think carefully enough that an engineer in the 2020s could still understand the result. Someone wrote instructions without knowing who might read them 50 years later. Someone labelled a wire, recorded a voltage, explained a memory address, or described an unusual backup mode. And that small act of documentation may eventually help save the mission. Voyager survives partly because its makers planned for failures, but also because later teams refused to treat old knowledge as disposable. There is something quietly practical about all of this. Contact with Voyager is not maintained by hope alone, and the spacecraft is not responding because it somehow wants to continue. It remains reachable because radio physics works across immense distances, because antennas can be aimed precisely, because weak signals can be extracted from noise, because plutonium produces heat for decades, because error-correcting codes protect information, and because human beings continue to organize shifts, reserve antenna time, test commands, and solve problems involving machinery older than many of the people solving them. When we say that we are still in contact with Voyager 1, the sentence sounds simple. In reality, it describes a chain of events extending across the solar system. A command begins as a decision made by a team on Earth. It is translated into a form understood by the spacecraft, checked for safety, sent to a transmitter, focused by a giant antenna, and released into space. The radio wave passes the Moon's orbit in a little more than a second. It crosses the distance to Mars in minutes, depending on where Mars happens to be. It continues past Jupiter, Saturn, Uranus, Neptune, and the region once dominated by the solar wind. Nearly a day later, a small dish on Voyager gathers a faint trace of it. The spacecraft responds using electrical power, produced from heat inside generators, launched in 1977. Its transmitter sends a signal back toward the inner solar system. That signal spreads and weakens for another long day until part of it reaches Earth. A deep space network antenna collects what it can. Receivers amplify it. Computers remove noise, decode patterns, correct errors, and deliver the result to the mission team. Only then does someone learn whether the distant machine followed the command. By November 2026, Voyager 1 will reach a distance of 1 light day from Earth. At that point, a radio message will require a full 24 hours to travel in one direction. Nothing about the spacecraft will suddenly change at that milestone. There is no wall or sign waiting in space, and Voyager will not pause to take a commemorative photograph. It will simply continue outward while the delay between question and answer grows a little longer. For tonight, though, we can remain with the signal itself. Somewhere beyond the planets, Voyager's antenna is still directed toward a sun that looks increasingly like another bright star. Near that sun is Earth, invisible to the spacecraft without specialized instruments, but known through calculations and orientation procedures. Voyager does not need to see our oceans, clouds, cities, or radio towers. It only needs to keep its dish aimed toward the correct point and continue sending its narrow stream of information. Long before Voyager 1 became a faint radio source in interstellar space, it began its journey in a much louder and more crowded place. On September 5th, 1977, a Titan III E-Centaur rocket lifted from Cape Canaveral in Florida, carrying the spacecraft away from Earth beneath a column of fire. At that moment, Voyager was not the farthest human-made object, not an interstellar explorer, and not yet the long-lived symbol of endurance it would eventually become. It was simply a new planetary probe beginning an ambitious mission toward Jupiter and Saturn, built by people who hoped it might work for several years and survive encounters with 2 enormous worlds. The idea that it would still be communicating nearly half a century later would have sounded less like an engineering plan and more like someone being unusually optimistic after too much coffee. Voyager 1 was one of 2 closely related spacecraft launched in 1977. Voyager 2 actually left Earth first, on August 20th, while Voyager 1 followed a little over 2 weeks later. The numbering can therefore seem backwards, rather like discovering that the second person in a queue was served first. Voyager 1 received its name because its faster route would carry it past Jupiter and Saturn before its companion. Although Voyager 2 had an earlier start, Voyager 1 quickly followed a shorter and more energetic path through the outer solar system. The timing of both launches was extremely important. During the late 1970s, Jupiter, Saturn, Uranus and Neptune were arranged in a rare pattern that allowed a spacecraft to travel from one giant planet to the next using gravity assists. This broad alignment occurs only about once every 176 years. It did not place the planets in a perfectly straight line, as diagrams sometimes suggest, but it positioned them so that a spacecraft could use each encounter to change its speed and direction, moving onward without carrying the enormous amount of fuel that would otherwise have been required. This opportunity had been studied years before Voyager was built. Engineers and mathematicians realized that a spacecraft passing close to a moving planet could borrow a small amount of the planet's orbital energy. The planet would lose an unimaginably tiny fraction of its motion, far too little to measure in any ordinary way, while the lightweight spacecraft could gain a substantial increase in speed. It is called a gravity assist, though the name can make it sound as if the planet is politely giving the spacecraft a push. In practice, the maneuver depends on carefully approaching the planet, falling into its gravitational field, curving around it and leaving in a new direction. Imagine rolling a small ball toward a moving train, except the train is a planet, the ball is a spacecraft, and trying this experiment near an actual railway would be strongly discouraged. From the Sun's point of view, the planet is moving rapidly along its orbit. If a spacecraft approaches from the correct direction, the planet's gravity bends the spacecraft's path and carries it forward for a time. When the spacecraft escapes, it can leave with greater speed relative to the Sun. No engine has to burn continuously. Gravity and orbital motion provide the change. This method turned the outer planets from isolated destinations into stepping stones. Without gravity assists, reaching Jupiter and Saturn would have required more fuel, larger rockets, or much longer travel times. Reaching Uranus and Neptune with the technology of the 1970s would have been especially difficult. The planetary alignment created the possibility of a grand tour, a single mission visiting all 4 giant worlds. Budget decisions eventually narrowed Voyager 1's official plan to Jupiter and Saturn, while Voyager 2 retained a path that could continue farther if the spacecraft remained healthy. Yet both missions benefited from the rare arrangement, and the course selected for Voyager 1 would send it through the planetary system at remarkable speed. After leaving Earth, Voyager did not travel straight upward, or simply move away from the Sun along a fixed line. Spaceflight is rarely that tidy. The spacecraft entered an orbit around the Sun, just as Earth does, but with a route designed to intersect Jupiter's path. Earth itself had already provided part of Voyager's starting speed. Because the launch occurred in the same direction that Earth travels around the Sun, the spacecraft carried the planet's orbital motion with it. The rocket then added more velocity, placing Voyager on a long outward curve. From the ground, a rocket launch lasts only minutes. For the spacecraft, however, those minutes determine years of travel. The launch vehicle had to place Voyager on the correct path with great accuracy. A small error at the beginning could become a very large error after hundreds of millions of kilometers. Mission controllers could make course corrections later using Voyager's thrusters, but the spacecraft carried only a limited amount of propellant. It was far better to begin close to the intended route than to spend precious fuel repairing a careless departure. Once the rocket stages had finished their work, Voyager separated and began operating on its own. Its large high-gain antenna was deployed and directed toward Earth. Scientific instruments were checked. The spacecraft began sending information about its condition, allowing engineers to confirm that power, communications, attitude control, and onboard computers were functioning. It was now a small independent machine in interplanetary space, relying on instructions transmitted from an increasingly distant planet. The first major destination was Jupiter, the largest planet in the solar system. Voyager 1 took about a year and a half to reach it, which was extraordinarily quick compared with many later missions. Jupiter lies more than 5 times farther from the Sun than Earth does, though the actual distance between Earth and Jupiter changes as both planets orbit. The spacecraft covered hundreds of millions of kilometers, guided by radio tracking and occasional corrections. As Voyager approached, Jupiter gradually changed from a bright point into a world. Cameras revealed bands of clouds, enormous storms, complex motions in the atmosphere, and the famous Great Red Spot. The spacecraft passed closest to Jupiter on March the 5th, 1979, moving through a system filled with powerful radiation and dozens of moons. Even then, Jupiter was known to be surrounded by a harsh environment, but Voyager's measurements showed just how intense it could be. One of the mission's most important discoveries occurred at Io, the innermost of Jupiter's 4 large Galilean moons. Images revealed active volcanoes throwing material high above the surface. Before Voyager, scientists had not directly observed active volcanism anywhere beyond Earth. Io looked nothing like a quiet, frozen moon. Its surface was being constantly reshaped by eruptions driven by tidal forces. Jupiter's gravity pulls strongly on Io, while the other large moons repeatedly alter its orbit. The moon is flexed and squeezed as it travels, generating heat within its interior. The discovery transformed the way scientists thought about small worlds. A moon did not need to be large like Earth or close to the Sun to remain geologically active. Gravitational relationships could provide energy. That lesson would later influence the study of Europa, Enceladus, and other moons that may contain oceans beneath their surfaces. Voyager also examined Jupiter's rings, which are much fainter than Saturn's, and returned detailed views of Europa, Ganymede, Callisto, and smaller satellites. It studied Jupiter's magnetic field and radiation belts, measured particles around the planet, and observed the atmosphere in ways that telescopes on Earth could not. During the encounter, the spacecraft collected far more information than it could send immediately. Data had to be stored, organized, and transmitted through the deep space network, where teams work through a steady flow of images and measurements. Yet Jupiter was not merely a subject for observation. It was also part of Voyager's transport system. The spacecraft approached on a carefully selected path and used the planet's gravity to increase its speed and redirect itself towards Saturn. A small difference in the Jupiter flyby would have changed everything that followed. The correct trajectory was not simply close to the planet. It had to pass through a narrow region at the correct time and angle. The gravity assist accelerated Voyager 1 to a speed that no rocket of the era could have produced on its own after launch. Jupiter acted as a turning point, bending the spacecraft's solar orbit outward. Voyager left the Jovian system, moving towards Saturn, its next destination, while Jupiter continued around the Sun almost entirely unaffected by the exchange. The planet is so massive compared with the spacecraft that the energy taken by Voyager made no meaningful difference to Jupiter's movement. It was similar to a grain of dust bouncing away from a moving lorry, except the lorry would not notice, and the grain of dust would leave with a carefully calculated scientific schedule. The journey from Jupiter to Saturn took roughly a year and 8 months. During that interval, mission controllers continued monitoring the spacecraft, sending commands, checking instruments, and refining the route. Voyager's cameras could observe Saturn from increasing proximity, but the detailed encounter would not occur until November 1980. Saturn presented a different kind of planetary system. Jupiter's size and storms dominate its appearance, while Saturn is surrounded by a ring system so broad and bright that the planet seems almost secondary. From Earth those rings look smooth, but Voyager revealed thousands of structures within them, There were gaps, narrow ringlets, waves, spokes, and complex patterns produced by interactions with Saturn's moons. The rings are made largely of water ice, with particles ranging from tiny grains to objects as large as buildings. Each piece follows its own orbit around Saturn. They are not a solid platform, despite what certain older science fiction illustrations might lead you to believe. Attempting to land on Saturn's rings would therefore be less like stepping onto a frozen road, and more like entering a high-speed field of ice, which would be an unfortunate place to discover that the brochure had been misleading. Voyager 1's closest approach to Saturn occurred on November 12, 1980. It studied the atmosphere, magnetic field, rings and moons. But one moon received particular attention. Titan, Saturn's largest moon, was already known to possess a thick atmosphere. Scientists wanted a close look because Titan was unlike any other moon then known. Its atmosphere is denser at the surface than Earth's and is composed mainly of nitrogen, with methane and other compounds. The mission planners chose a trajectory that carried Voyager 1 close to Titan. The encounter provided valuable measurements, confirming the atmosphere's density and composition, while revealing that thick haze completely hid the surface from the spacecraft's visible light cameras. Voyager could not see the lakes, dunes, channels, and icy landscapes that later missions would discover, but its data established Titan as one of the most interesting worlds in the solar system. That close pass came with a major consequence. Titan's gravity changed Voyager 1's path, directing it above the plane in which most planets orbit. The trajectory ended any possibility that Voyager 1 might continue to Uranus and Neptune. Its planetary tour was finished. Voyager 2, following a different route, would go on to visit both worlds, becoming the only spacecraft ever to fly past either of them. Voyager 1, meanwhile, was sent away from the main planetary plane on a path that would eventually carry it into interstellar space. This was not an accident or an unexpected failure. The Titan encounter had been deliberately prioritized. Scientists considered the moon important enough to sacrifice the option of further planetary flybys for Voyager 1. There was also practical value in having Voyager 1 leave the planetary plane. The spacecraft could study regions above it and travel toward the outer boundary of the Sun's influence, along a different direction from Voyager 2. Once Saturn receded behind it, Voyager entered what was called the interstellar mission. That name described a goal rather than an immediate location. The spacecraft was still deep inside the heliosphere, the enormous region filled by the solar wind. It would take more than 3 decades to reach the boundary where the solar wind's dominance gave way to the conditions of interstellar space. The solar wind is a continuous flow of charged particles released by the Sun. It moves outward in all directions, carrying part of the Sun's magnetic field with it. As this material expands, it creates a vast protective bubble around the planets. That bubble is not perfectly spherical. The Sun moves through the surrounding interstellar material, and the heliosphere responds to that motion, though its exact shape remains an active subject of research. Voyager continued outward at about 17 kilometers per second relative to the Sun. That is more than 60,000 kilometers per hour, fast enough to circle Earth in well under an hour if roads, oceans, air resistance, and several other inconvenient details were removed. Yet space is so large that even this speed produces a slow-looking journey on a map of the solar system. Voyager requires years to cross distances that light covers in hours. Its velocity gradually made it the most distant human-made object. Pioneer 10, launched in 1972, had previously held that distinction. Voyager 1 overtook it in 1998 because its gravity-assisted route had given it greater speed. Pioneer 10 was still travelling outward, but Voyager was moving faster and in a different direction. From that point onward, Voyager 1 led the small collection of spacecraft escaping the solar system. The phrase escaping the solar system requires a little care. There is no single, universally agreed edge. Voyager has escaped the region of the planets and is moving too quickly for the Sun's gravity to bring it back. It has also crossed the heliopause, which marks the outer boundary of the heliosphere. Yet it has not passed through the Oort cloud, the distant reservoir of icy objects thought to surround the Sun. Reaching its inner portion may take centuries, and crossing the entire cloud could require tens of thousands of years. So, when people say Voyager has left the solar system, they usually mean it has entered interstellar space beyond the heliopause. That is true. But if the solar system includes every object gravitationally associated with the Sun, Voyager still has an enormous distance to travel. Space is very good at providing more edge after you thought you had already reached the edge. During the 1990s and early 2000s, Voyager's instruments recorded changes in particles and magnetic fields as the spacecraft moved farther from the Sun. The solar wind became less dominant. Cosmic rays coming from beyond the heliosphere became easier to detect. Scientists knew the spacecraft was approaching a region where the outward flow from the Sun would begin to slow under pressure from interstellar material. In December 2004, Voyager 1 crossed the termination shock. This is the region where the solar wind, which had been travelling faster than the speed of sound within the plasma, slowed abruptly. The crossing occurred about 94 astronomical units from the Sun. 1 astronomical unit, or AU, is the average distance between Earth and the Sun, roughly 150 million kilometres. Voyager was therefore about 94 times farther from the Sun than Earth is. Beyond the termination shock lay the heliosheath, a turbulent outer region of the heliosphere. Voyager spent years travelling through it. The mission team watched for signs that the spacecraft had finally crossed the heliopause. They expected changes in the number and type of charged particles, along with possible changes in magnetic field direction. The answer did not arrive as a single dramatic announcement from the spacecraft. Voyager did not pass a sign saying, "Welcome to interstellar space. Please reduce speed." Instead, measurements changed in stages. In 2012, the number of particles originating from inside the heliosphere dropped sharply, while galactic cosmic rays increased. After careful analysis, scientists concluded that Voyager 1 had crossed the heliopause on August 25, 2012, at a distance of about 121 astronomical units from the Sun. Humanity had placed an operating spacecraft in interstellar space for the first time. Even then, Voyager remained within the gravitational influence of the Sun and far from any other star. Interstellar space is not a crowded region filled with nearby suns, colourful clouds, and convenient stopping points. It is extremely thin. The spacecraft travels through sparse particles and magnetic fields, with no planet or star close enough to visit. Its next approach to another star will not occur for tens of thousands of years, and even then it will pass at a great distance. Voyager's motion is also not directed toward a carefully selected destination beyond the solar system. The spacecraft was designed to visit planets, not another star. Its present route is simply the path produced by its launch and gravity assists. In about 40,000 years, it will pass within roughly 1.6 light-years of a star called Gliese 445. That is closer than Voyager will be to the Sun by then, but still far too distant to count as a visit. 1 light-year is nearly 9.5 trillion kilometres, so 1.6 light-years leaves plenty of room for a very quiet neighbourhood. By that time, Voyager will almost certainly have stopped operating. Its electrical power will fade long before the encounter, and its transmitters will fall silent. The spacecraft itself may continue moving for millions or billions of years, unless it collides with something, which is extremely unlikely in such empty space. It will circle the centre of the Milky Way as the Sun does, following its own galactic orbit. The golden record attached to Voyager was included with that long future in mind. It contains sounds, images, music, greetings in many languages, and information intended to describe Earth and humanity. The record is protected by a metal cover engraved with instructions showing how it might be played and how the location of the solar system could be determined. No one involved in the mission expected aliens to find it easily. Space is far too large, and Voyager is far too small. The record was partly a message to possible discoverers, and partly a statement about the people who sent it. It says, in effect, that one small species on one planet became curious enough to build a machine and send it outward. We included ocean waves, birds, heartbeats, human voices, and music, because those were among the things we considered worth preserving. It is a small archive travelling through a region where there may be nobody to receive it. For the mission team, however, Voyager's greatest value has never depended on a future discovery by extraterrestrial life. Its immediate purpose has always been science. It transformed Jupiter and Saturn from distant telescope targets into observed worlds with complex moons, rings, storms, magnetic fields, and active geology. It then became a probe of the heliosphere's outer regions, and finally, an instrument operating in interstellar space. The distance it has travelled can be expressed in kilometres, but the number becomes difficult to absorb. More useful comparisons often involve the time required for light to cross the gap. Light from the Moon reaches Earth in about 1.3 seconds. Light from the Sun takes about 8 minutes and 20 seconds. Depending on the positions of the planets, a signal from Mars may take several minutes, while one from Neptune requires hours. Voyager 1 is now so far away that its messages need almost a full day to travel one way. That long delay did not appear suddenly. It grew gradually throughout the mission. Near Earth, communication felt nearly immediate by deep space standards. At Jupiter, the one-way delay was measured in tens of minutes. At Saturn, it exceeded an hour. As Voyager moved outward, the delay stretched to several hours, then half a day, then most of a day. Engineers adapted their procedures as conversation became correspondence. Its increasing distance also weakened the radio signal. Radio waves spread outward as they travel, distributing their energy over a larger and larger area. The farther Voyager moved, the smaller the fraction intercepted by an antenna on Earth. The spacecraft's transmitter did not become stronger to compensate. Its available power was declining. Continued communication therefore depended increasingly on large ground antennas, sensitive receivers, careful scheduling, and advanced processing. This creates a curious situation. Voyager became more scientifically unusual as it moved farther away, but also harder to hear. It reached a region no other active spacecraft had sampled, just as the connection needed to retrieve those measurements grew weakest. Every additional kilometre increased both its value and its difficulty. The physical journey also shaped the spacecraft itself. Radiation, temperature changes, and decades of operation affected its components. Thrusters fired thousands of times to maintain orientation. Electrical power declined steadily. Some instruments were turned off because their planetary work was complete, while others were preserved for studies of particles and fields. Backup systems became primary systems. Procedures written for short-term emergencies became regular methods of operation. Voyager was never expected to remain young. The mission survived because its design allowed it to become simpler. It did not continue doing everything it did at Jupiter. Its cameras were switched off after the planetary encounters because there was little nearby to photograph, and because operating them consumed power and resources. The spacecraft gradually became less like a general planetary observatory and more like a focused interstellar monitoring station. One of its final sets of photographs included the famous view known as the pale blue dot. On February 14, 1990, Voyager 1 turned its camera back toward the planets and photographed the solar system from about 6 billion kilometers away. Earth appeared as a tiny point of light, less than a single pixel caught in a ray of scattered sunlight. The image did not reveal continents, oceans, weather systems, or signs of civilization. Everything human beings had built, argued about, loved, feared, collected, misplaced, and attempted to remain occupied that almost invisible dot. After the family portrait was completed, Voyager's cameras were turned off permanently. There was no reason to keep using them in the darkness ahead, and conserving power mattered more than photographing empty space. The spacecraft continued onward without visual navigation in the familiar sense. It maintained its orientation using sensors and calculated references, keeping its antenna aimed toward Earth. From our point of view, Voyager moved beyond the planets and became a distant traveller. From Voyager's point of view, nothing was watching the journey unfold. It had no awareness of Jupiter growing behind it, or Saturn fading into a point. It did not know when it became the farthest human-made object, or when newspapers on Earth celebrated its entry into interstellar space. It simply followed commands, measured its surroundings, and transmitted data according to programs stored in old electronic memory. That steady operation is perhaps more remarkable than a dramatic act would have been. The spacecraft did not reach its record distance through one enormous leap. It reached it by moving continuously for decades. Every second carried it another 17 kilometers or so from the Sun. Every day added roughly 1.5 million kilometers. Every year placed hundreds of millions more kilometers between the spacecraft and the people listening to it. The engineers who launched Voyager watched it cross distances that no earlier working spacecraft had reached. Many retired while it continued. New team members arrived who had been children or had not yet been born when the rocket left Florida. The mission outlasted careers, computer systems, communication technologies, and entire generations of household electronics. Devices once considered futuristic became museum pieces, while Voyager's original hardware continued operating beyond the heliopause. Its route from Earth to interstellar space therefore connects several very different periods of exploration. It began during the first great era of robotic planetary missions, when detailed images of the outer planets did not yet exist. It passed Jupiter and Saturn before reusable spacecraft had become common. It crossed the termination shock in an age of broadband internet. It entered interstellar space when smartphones were already ordinary. It remains in contact during a period when engineers can run simulations on computers vastly more powerful than anything available to the original designers. The spacecraft has not been upgraded during any of this. The distance record belongs not to a machine that became faster, but to one that never stopped. Its initial speed, shaped by the rocket and the giant planets, has carried it farther year after year. Nothing is chasing closely enough to overtake it soon. Other probes are also leaving the solar system, including Voyager 2, Pioneer 10, Pioneer 11, and New Horizons, but their directions and speeds differ. Voyager 1 remains the most distant. There is no practical reason to describe that distance as a race. The spacecraft are not heading toward the same finish line, and no trophy is waiting beyond the heliosphere. Yet Voyager's position gives a simple measure of human reach. Of all the objects our species has built, this one has travelled farthest from home while still reporting back, and reporting back is the part that changes the journey from a piece of history into an ongoing mission. A silent spacecraft could continue drifting through interstellar space and remain physically impressive, but an operating Voyager is something more useful. It tells us what it encounters. It sends measurements from beyond the solar wind. It allows Earth to compare conditions near the planets with conditions outside the heliosphere. The journey explains why communication is now so difficult. Every gravity assist, every year of outward motion, and every boundary crossed has increased the space through which Voyager's signal must travel. The same path that made it the farthest human-made object also reduced its transmission to one of the weakest messages we regularly attempt to receive. At first, the phrase radio signal can make Voyager's communication sound more substantial than it really is. You might picture a clear beam extending from the spacecraft to Earth, rather like the light from a torch aimed across a dark room. The actual transmission is much less dramatic. Voyager 1 produces a low-power radio wave, directs it toward the general location of Earth, and allows it to spread across space for almost an entire day. By the time a tiny part of that wave reaches us, it is so weak that ordinary radio equipment would never notice it. Earth does not hear a loud electronic voice calling from the distance. It searches for a carefully predicted pattern hidden inside a great deal of noise. That pattern begins inside Voyager's telecommunication system. Electrical energy from the spacecraft's aging power supply is sent to a radio transmitter, which creates a stable electromagnetic wave. Electromagnetic waves include visible light, infrared radiation, ultraviolet light, microwaves, and radio signals. They differ mainly in their frequencies and wavelengths, but they all travel through a vacuum at the speed of light. This is fortunate because there is almost no matter between Voyager and Earth to carry an ordinary sound. Sound is a vibration moving through material. It can travel through air, water, metal, or other substances, but it cannot cross a vacuum by itself. If Voyager possessed a large loudspeaker and played a cheerful message into interstellar space, nobody on Earth would hear it. There would be no air available to pass the vibration from one place to the next. Radio waves need no such material. They are changing electric and magnetic fields that can move through empty space, which makes them ideal for communicating with a spacecraft beyond the planets. Voyager normally sends its information to Earth through an X-band radio transmitter. The downlink frequency is around 8.4 GHz, meaning that the electromagnetic field oscillates roughly 8.4 billion times each second. You do not need to count those oscillations before going to sleep. The equipment on Earth is quite happy to handle that part for you. What matters is that this particular frequency sits within a range commonly used for deep space communication and can be generated, directed, received, and measured with great precision. The transmitter itself operates with remarkably little power. Voyager's X-band transmitter has been described as producing about 12.5 watts. Some descriptions of the complete radio output use figures closer to 20 watts, depending on exactly which equipment and operating conditions are being discussed. But either way, this is not the power of a major broadcasting station. It is in the general range of a small household light. Yet Voyager attempts to use that modest electrical output to send information across more than 25 billion kilometers. Of course, a light bulb spreads most of its energy around a room in many directions. Voyager cannot afford to do that. It uses its large high-gain antenna to concentrate radio energy into a narrower beam. This antenna is the broad white dish that gives the spacecraft its most recognizable appearance. It measures about 3.7 meters across, making it wider than many bedrooms but still very small compared with the giant dishes waiting on Earth. The antenna's curved shape is important. Radio waves created by the transmitter are directed toward the dish and reflected outward in a more organized beam. The same basic principle is used by satellite television dishes, radar antennas, and radio telescopes. A parabolic reflector can collect waves arriving from one direction, or concentrate transmitted energy into a chosen direction. Turn the dish one way and it becomes a listener. Feed it from the correct point and it becomes a sender. Voyager's beam is narrow compared with a signal broadcast equally in every direction, but it is not a perfectly straight line with sharp edges. Radio energy naturally spreads. The beam from Voyager's high-gain antenna is about half a degree wide, roughly the apparent width of the full moon in Earth's sky. That sounds very precise until you extend the beam across tens of billions of kilometers. A tiny angle becomes an enormous area at that distance. Imagine drawing two lines that begin close together but slowly separate. After 1 meter, the gap may be small. After a kilometer, it is larger. After billions of kilometers, the same angle produces a beam broad enough to cover a vast region surrounding Earth's orbit. Voyager does not have to strike a receiving antenna, as though throwing a dart at one exact point. It must aim its radio beam toward the inner solar system accurately enough that Earth remains somewhere inside it. Even with that assistance, the spacecraft's orientation matters enormously. If the high-gain antenna turns several degrees away from Earth, The signal can become too weak to decode or may disappear completely. Voyager's small attitude control thrusters therefore fire occasionally to correct its pointing. The spacecraft uses references including the Sun and selected stars to maintain its orientation. These adjustments keep the antenna facing the point where Earth is expected to be. Earth is not stationary, of course. It moves around the Sun at nearly 30 kilometers per second, while the Sun itself travels through the Milky Way and Voyager continues outward along its own path. The mission team must calculate where Earth and Voyager will be when a transmission arrives, not merely where they are when it leaves. Fortunately, their motions are predictable. The communication system does not have to chase Earth blindly across the sky. Navigation specialists use radio tracking, orbital calculations, and decades of trajectory data to estimate the geometry with great accuracy. Once Voyager transmits, the radio wave begins its long crossing. Nothing carries it or guides it through space. There are no relay stations placed beyond Saturn, no communication satellites waiting near Neptune, and no interstellar telephone cables running beside the spacecraft. The signal simply travels outward at the speed of light. For the first second, it moves almost 300,000 kilometers. That would take it most of the way from Earth to the Moon. After 8 minutes or so, it has crossed the average distance between Earth and the Sun. A few hours later, it has passed the scale of the planetary system. Still, Voyager is so far away that the wave must continue for more than 23 hours before reaching Earth. During that journey, the radio energy becomes steadily more diluted. This is one of the central problems in deep space communication. The transmitter does not lose power because space is actively absorbing everything along the route. Interstellar space is transparent enough at the frequency Voyager uses. Instead, the energy spreads across a growing area. A useful comparison is the light from a lamp. Stand close to the lamp and its light appears bright. Move farther away and the same amount of energy must illuminate a wider region. Nothing necessarily happened to the lamp. Its output is simply distributed more thinly. Radio signals follow a similar rule. Double the distance and the energy is spread over roughly 4 times the area. Increase the distance by 10 and the same transmitted power is distributed across about 100 times the area. Voyager's increasing separation from Earth therefore creates a severe penalty. Every year, the signal must cross a little more space, and its power at Earth becomes a little lower. The transmitter cannot simply turn itself up to compensate. Voyager's available electricity is already declining, and the radio hardware has fixed limits. Much of the mission's communication improvement must consequently happen at the receiving end. By the time Voyager's signal reaches Earth, the amount of power collected by a deep space network antenna can be around 1/1000,000,000,000 of a watt. Written as a decimal, that involves a long row of zeros before anything interesting appears. It is far weaker than the power used by a digital wristwatch and far below what any normal radio would be designed to detect. The signal is not merely faint in an empty and perfectly silent environment. It arrives among many other sources of electromagnetic energy. The atmosphere contributes noise. The ground and nearby equipment radiate heat. Electronic components inside the receiver produce their own random fluctuations. Natural radio sources exist in space. The Sun can interfere when the geometry places it close to the line between Earth and Voyager. Human technologies create transmissions that must be avoided or filtered. Even empty space is not completely silent at radio frequencies. The universe contains background radiation, and every physical receiver above absolute zero produces some thermal noise. The task is therefore not to detect energy where there was previously nothing. It is to recognize Voyager's organized signal within a much larger mixture of unrelated energy. This is where knowing what to expect becomes extremely helpful. The Deep Space Network does not scan every frequency in every direction, while hoping Voyager happens to appear. Engineers know approximately where the spacecraft is in the sky. They know the frequency its transmitter should be producing. They know the data format, the coding method, and the likely Doppler shift caused by motion between the spacecraft and the receiving station. You may have heard the Doppler effect when an ambulance passes. The siren sounds higher as the vehicle approaches and lower as it moves away. The sound source has not deliberately changed its note. The motion alters how frequently the waves reach you. Radio waves behave in a comparable way. As Voyager and Earth move relative to each other, the received frequency shifts slightly. Earth's rotation also moves the antenna toward or away from the spacecraft during a tracking session, adding another small change. These shifts are predictable. Computers calculate how the frequency should drift over time, allowing receivers to follow the signal. A narrow search can reject much of the energy arriving at other frequencies. It is like trying to hear one musical note in a crowded room while already knowing the pitch, the direction, and approximately when it will begin. The note remains quiet, but the search becomes far more manageable. At the center of Voyager's transmission is a carrier wave. The carrier is the stable radio signal used to transport information. Data are added by making controlled changes to properties of that wave. Depending on the system, information can be encoded through changes in phase, frequency, amplitude, or combinations of these. Voyager's communication methods were designed for reliability, not for the sort of speed expected from modern internet connections. The distinction between the carrier and the data carried upon it becomes important when a spacecraft develops a fault. Ground antennas may detect the carrier even when they cannot decode useful telemetry. In that situation, engineers know the transmitter is still operating and the spacecraft is probably alive. They may even measure the carrier's frequency and use it to confirm the craft's movement, but the organized stream describing temperatures, voltages, instrument readings, and computer status may be missing or corrupted. It is similar to hearing that someone is speaking at the far end of a poor telephone connection without understanding the words. The presence of a voice tells you the call has not ended. Recovering the meaning is a separate problem. Voyager 1 demonstrated this distinction during its communication problem that began in late 2023. The spacecraft continued producing a radio signal, but the returning engineering and scientific information repeated an unusable pattern. The transmission path still worked. The high-gain antenna remained pointed toward Earth, and the deep space network could hear the spacecraft. Something within the system responsible for preparing the data was failing to produce meaningful content. That faint carrier gave the team a place to begin. Had the signal vanished entirely, they would have needed to consider failures in the transmitter, power supply, attitude control, antenna pointing, command reception, or several other systems. Because the carrier remained detectable, attention could turn toward the computers and memory involved in organizing telemetry. Months of carefully delayed testing eventually led engineers to identify damaged memory and move software instructions to functioning locations. Once information is placed onto the radio signal correctly, Voyager sends it at a rate that would test the patience of almost any modern device. The usual real-time science data rate is about 160 bits per second. Since 8 bits make 1 byte, that works out to around 20 bytes each second. In 1 minute, the spacecraft may deliver only about 1,200 bytes, before accounting for formatting and other communication needs. A single ordinary photograph from a modern phone can contain several million bytes. Sending such an image at Voyager's current rate could take days, and that assumes the spacecraft still had an operating camera and enough memory to handle it, which it does not. Streaming video would be so unrealistic that the loading symbol might qualify as a permanent monument. Fortunately, Voyager's remaining scientific instruments do not produce holiday photographs or high-definition films. They measure things such as particles, magnetic fields, and plasma waves. These measurements can often be represented by compact numerical values. The spacecraft does not need to send a detailed picture of every charged particle passing nearby. It can report counts, energies, directions, field strengths, frequencies, and changes over time. Engineering telemetry is similarly efficient. A small number may describe the voltage on a power line. Another value may represent the temperature of a component. Individual bits can indicate whether a switch is on or off, whether a fault flag has been set, or which operating mode the spacecraft is using. When communication is this limited, each bit is assigned a purpose. The uplink from Earth is also slow. Voyager receives commands through S-band radio at about 16 bits per second. Earth can transmit with far more power than the spacecraft, using enormous antennas and strong amplifiers, but Voyager's receiving system remains a product of the 1970s. Sending instructions slowly makes them easier for the spacecraft to detect and reduces the chance that noise will turn one command into another. A command does not usually contain a long explanation. Engineers translate their intentions into tightly defined digital sequences recognized by Voyager's computer command system. One code might change a mode, another might cause a memory readout, switch an instrument, alter a heater, or prepare a sequence of later actions. Larger software changes require many commands and careful organization. Because the uplink is slow, and each instruction takes almost a day to arrive, mission controllers do not operate Voyager as though steering a remote-controlled car. They cannot watch it begin to drift and immediately press a button to correct the motion. The spacecraft must perform many tasks autonomously. Commands may be stored for execution later, and onboard fault protection routines can react when certain measurements move outside safe limits. Reliability begins before the message leaves Earth. Commands are checked repeatedly because a single error can be difficult to reverse. Engineers use simulations and test equipment to predict how the spacecraft will interpret an instruction. They examine whether the command might conflict with another operating mode, consume too much power, change the spacecraft's orientation, or activate equipment that has become unsafe with age. After these reviews, the command is encoded with additional structure so that Voyager can recognize valid information. The spacecraft does not treat every random radio fluctuation as an order. That would produce a very nervous probe. The signal includes synchronization patterns, addresses, and checks designed to separate intentional commands from noise. Returning telemetry also receives protection. Voyager was the first spacecraft mission to use Reed-Solomon error-correcting coding, a method that adds carefully calculated extra symbols to the data. Those extra symbols allow computers on Earth to detect and correct certain errors introduced during transmission. A simple version of error protection might repeat every bit several times. If the message contained 111 instead of a single one, and noise changed one copy to 0, the receiver could examine the majority and conclude that the original bit was probably 1. Real error-correcting codes are much more efficient. They use mathematical relationships across blocks of data, allowing missing or damaged portions to be recovered without blindly repeating everything. This matters because Voyager's signal is close to the detection limit. Some bits will inevitably arrive with uncertainty. The receiver may struggle to decide which state was intended. Error correction turns a fragile stream into something more dependable, although it cannot repair unlimited damage. If too much information is lost, the block may remain unusable. The Deep Space Network can also improve reception by allowing several antennas to listen together. This technique is known as arraying. Each dish receives Voyager's signal along with its own mixture of noise. Because the antennas know the expected timing and frequency, their observations can be combined. Voyager's signal reinforces itself, while some of the unrelated noise does not line up in the same way. In 2024, 6 antennas at the Madrid Deep Space Communications Complex were arrayed together during work to recover Voyager 1's usable telemetry. Combining antennas effectively creates a larger receiving system without requiring one impossibly wide dish to be built overnight. A 70-meter antenna remains extremely valuable, but several 34-meter dishes can contribute additional collecting area and improve sensitivity. Receiving dishes must point with extraordinary precision. A 70-meter antenna is a moving structure weighing thousands of tons, yet it has to track a source that cannot be seen through an ordinary telescope. Motors turn the entire dish slowly as Earth rotates, keeping Voyager within the antenna's narrow field of view. Computer models compensate for the spacecraft's position, Earth's motion, and the geometry of the tracking station. The dish reflects incoming radio waves toward a receiver positioned near its focus. The receiver's first job is to amplify the signal without adding too much noise of its own. This is more difficult than it sounds. Every amplifier introduces some disturbance. Deep space receivers therefore use specialized low-noise equipment, sometimes cooled to very low temperatures so that thermal motion inside the electronics contributes less interference. After amplification, the signal passes through additional processing. The system searches for the carrier, follows its Doppler shift, extracts the modulation, identifies the digital symbols, applies error correction, and reconstructs data frames. Those frames are then sent through ground networks to mission operations and scientific teams. No person sits beside the dish wearing headphones and suddenly hears Voyager appear. The signal is not converted into a voice because there is no voice aboard the spacecraft. What engineers see are measurements, frequency plots, streams of binary data, and indicators showing whether the receiver has locked onto the transmission. There can still be a satisfying moment when lock is achieved. Before that point, the system may be searching around the expected frequency. Once it recognizes the carrier and begins following it reliably, the receiver can attempt to decode telemetry. A small status change on a screen may therefore represent the successful completion of a journey lasting nearly a day. The information received during a tracking pass may describe events that happened many hours earlier. Even the word now becomes complicated. When engineers see Voyager's current temperature on a display, they are actually seeing the temperature recorded when the signal began its journey toward Earth. By the time the value appears on the ground, Voyager has travelled more than 1 million additional kilometres. Mission controllers must always work with this delayed version of the spacecraft. They never know its exact present condition through direct observation. They know what it was doing almost a day ago, along with what commands it should have received since then. Using those records and their understanding of the spacecraft, they infer what is probably happening now. This delay would be inconvenient in an emergency. Suppose Voyager detects a problem and enters a protective mode. The first indication cannot reach Earth for more than 23 hours. Engineers then analyse the data, design a response, verify it, and transmit a command that needs another 23 hours to arrive. Even in the best case, the spacecraft may need to manage the fault alone for several days. The radio connection is therefore not a continuous conversation in the ordinary sense. It is a sequence of delayed reports and carefully prepared instructions. Earth speaks, waits, listens, studies, and speaks again. Voyager responds according to its programming, without knowing whether anybody is currently receiving the answer. The Deep Space Network does not listen to Voyager every minute of every day. Antenna time must be shared among many missions, and each site can track only spacecraft visible above its horizon. The Voyager mission typically receives several hours of real-time tracking data per spacecraft each day. During those scheduled periods, the antennas collect science and engineering information. At other times, Voyager may continue transmitting into space, while no suitable Earth antenna is assigned to listen. Most of that radio energy will never encounter anything capable of detecting it. The beam passes Earth's region and continues outward, growing weaker. A tiny portion enters a deep space network dish. An even tinier portion is transformed into electrical signals, decoded and saved. From the transmitter's original few watts, humanity recovers just enough organized energy to understand what a machine is measuring beyond the heliosphere. That may be the most surprising part of the radio whisper. We do not defeat distance by making Voyager shout. Voyager cannot shout. We maintain contact by controlling every part of the communication chain, choosing a useful frequency, concentrating the transmission with a dish, predicting the spacecraft's direction, sending data slowly, adding error correction, building enormous receiving antennas, reducing electronic noise, and combining observations when one dish is not enough. The signal remains weak because physics gives it no special treatment. Radio waves spread whether the message is important or not. Light speed remains finite no matter how urgently engineers want an answer. Thermal noise does not politely become quiet when Voyager develops a fault. Contact continues because the mission was designed around these limits rather than expecting them to disappear. Inside the received stream are numbers that may look ordinary once displayed on a computer. A temperature may be represented by a few digits. A particle detector may report a count. A voltage may appear beside the name of a circuit. Nothing on the screen shows the enormous distance crossed by those bits, yet each value began aboard a spacecraft beyond the Sun's protective bubble, was placed onto an X-band carrier by electronics built in the 1970s, and travelled for almost a full day before reaching Earth. The weak signal tells us more than the state of an instrument. Its frequency helps navigators study Voyager's motion. Small changes can reveal how the spacecraft is travelling relative to Earth. The radio connection provides both communication and tracking, allowing mission teams to update their knowledge of its trajectory. Maintaining that link will grow harder. Voyager continues moving away, its radio signal continues weakening, and its electrical supply continues declining. Ground technology can compensate for some of these changes, but not forever. Larger arrays, improved receivers, and better processing can extract information from very weak transmissions, yet there is always a limit at which the signal becomes indistinguishable from noise, or the spacecraft can no longer produce it. For now, the carrier is still there. It arrives not as a loud announcement but as a precise disturbance at a known frequency, emerging from the direction calculations say Voyager should occupy. Computers follow its slow drift. Antennas collect it. Error-correcting systems rebuild its damaged pieces. Engineers transform the recovered bits into a picture of a machine they cannot see. To receive Voyager one's radio whisper, Earth needs something far larger and more sensitive than an ordinary satellite dish. A household dish may be perfectly capable of collecting television signals from satellites orbiting a few tens of thousands of kilometers above the planet, but Voyager is more than 25 billion kilometers away. Its transmission has spread across an enormous area. Its power supply is slowly declining, and its data arrive at only a tiny fraction of the speed we now expect from everyday communications. A normal antenna would not hear anything useful. Even many professional antennas would struggle. The task belongs to the Deep Space Network, a worldwide system of giant radio dishes built to communicate with spacecraft at the Moon, the planets, and far beyond them. The name can sound as though the network exists somewhere in space, perhaps floating beside a convenient interplanetary junction. In reality, every Deep Space Network antenna stands firmly on Earth. The system has 3 main complexes positioned around the world: Goldstone in California's Mojave Desert, Madrid in Spain, and Canberra in Australia. They are separated by roughly 120 degrees of longitude, allowing Earth's rotation to bring one site into view as another begins to lose sight of a distant spacecraft. Voyager's signal may set below the horizon at one complex, but another part of the network can soon take over. Earth turns, the antennas continue tracking, and the connection is passed around the planet. This arrangement solves a simple but unavoidable problem. Radio waves can travel through the atmosphere and across interplanetary space, but they cannot pass directly through the solid body of Earth. When Voyager is below the horizon from California, Goldstone cannot point an antenna through several thousand kilometers of rock and listen from the other side. Building a larger dish would not help. The planet remains rather difficult to see through. By placing facilities in North America, Europe and Australia, NASA created a system that can follow spacecraft across the sky as Earth rotates beneath them. The complexes were not built in the centers of large cities. They are located in relatively remote regions where hills, distance, and local regulations help reduce interference from ordinary radio transmitters. Mobile phones, television stations, radar systems, wireless networks, and many other technologies fill the modern environment with radio energy. That energy is useful when you're trying to connect a laptop or listen to a broadcast, but less helpful when you are searching for a signal billions of times weaker than familiar electronic emissions. Goldstone lies among the dry hills and open spaces of the Mojave Desert, far from the densest parts of Los Angeles. The Madrid complex stands in the countryside west of the Spanish capital, surrounded by land that offers some protection from urban radio noise. Canberra's antennas are located at Tidbinbilla, in a quiet region outside the Australian capital. Each setting provides open sky, stable ground, and enough distance from major transmitters to give the receiving equipment a chance of noticing deep space signals. Complete silence is impossible. The antennas themselves contain electronics that generate small amounts of noise. The ground radiates heat. The atmosphere contributes interference, and natural radio energy arrives from the sun, planets, stars, galaxies, and the background of the universe. The Deep Space Network does not remove every unwanted signal. Instead, it reduces what it can, measures what remains, and searches very narrowly for the expected transmission. That search begins with calculations performed before the antenna moves. Navigators estimate where Voyager will appear in the sky from a particular station at a particular time. They also predict the radio frequency that should reach Earth after accounting for the Doppler effect. Voyager is moving away from the Sun, Earth is orbiting the Sun, and the receiving station is being carried around by Earth's rotation. All those motions slightly alter the frequency detected on the ground. Operators do not point a dish toward a broad region labelled interstellar space and hope for the best. The network receives a detailed set of pointing predictions and frequency predictions. The antenna turns toward a precise location, while the receiver searches within a narrow range around the expected signal. As the tracking session continues, both the direction and expected frequency change. Computers update the antenna's motion and follow the carrier as it drifts. The largest dish at each Deep Space Network complex measures 70 meters across. That is about the length of a passenger aircraft's wingspan and close to the width of a large football pitch. Standing near one, you would not see a delicate scientific instrument that looks as though it ought to be kept inside a laboratory. You would see an enormous curved structure of metal, supports, platforms, motors, cables, and machinery. Yet the surface must maintain the precise shape required to reflect radio waves toward its focus. Each 70-meter antenna can rotate from side to side and tilt upward or downward. The moving structure weighs thousands of tons, but it can follow a spacecraft across the sky with extreme accuracy. Bearings, motors, gears, control systems, and counterweights work together to move the dish smoothly. If it jerks, flexes unpredictably, or points slightly away from its target, part of the already weak signal may be lost. Wind also matters. A large radio dish presents an enormous surface to moving air. Strong winds can distort the structure, increase pointing errors, or make operation unsafe. Engineers must account for the way gravity and temperature affect the antenna as it changes position. The metal structure warms in sunlight and cools at night. Different parts may expand or contract by small amounts, altering the dish's shape. Calibration models help compensate for these changes. Voyager's radio waves strike the curved surface and reflect towards specialized receiving equipment. Depending on the antenna design, the energy may be directed toward a feed system mounted near the dish or guided through a series of radio frequency mirrors into a protected equipment room. Many of the newer 34-meter antennas use a beam waveguide design. Instead of placing all the sensitive equipment high on the moving structure, mirrors carry the radio signal down through the antenna's center into rooms below ground level. This arrangement makes maintenance and upgrades easier. Engineers can reach receivers, amplifiers, and other hardware without climbing into a cramped moving cabin, suspended above a giant dish. The equipment can also be kept in a controlled environment, protected from weather and sudden temperature changes. Deep space communication depends on extremely sensitive electronics, and those electronics tend to behave better when they are not being roasted by desert sunlight one afternoon and chilled through the night. The first stages of the receiving system are designed to add as little noise as possible. Voyager's signal is already close to the limit of detection. A noisy amplifier could bury it completely. Deep space network receivers therefore use low-noise components, some of which are cooled to very low temperatures. Cooling reduces random thermal motion inside the electronics, allowing the faint organized signal to stand out more clearly. The received power from the Voyager spacecraft is about 20 billion times weaker than the power used by a digital wristwatch. That comparison may sound almost too strange to be useful, because a wristwatch already consumes very little energy. Yet the deep space network can collect Voyager's signal repeatedly, identify its carrier frequency, and recover information from it. The antennas do not gather much energy, they gather enough energy, and the processing system knows exactly what to do with it. The 70-meter dishes receive the greatest attention because of their size, but the network also contains several 34-meter antennas at each complex. These smaller dishes are still huge by ordinary standards. A 34-meter diameter is wider than the length of two large buses placed end to end. They support many missions and can sometimes be combined to improve reception. This combining process is called arraying. Two or more antennas point toward the same spacecraft and record the same transmission. Their signals are then aligned and added together. Voyager's carrier appears in each observation with a predictable timing relationship, so it reinforces itself when the recordings are combined. Much of the random noise differs from antenna to antenna and does not add as neatly. Arraying increases the network's effective collecting area. 4 34-meter antennas can provide roughly the receiving capability of one 70-meter dish under suitable conditions. Engineers may also combine a 70-meter antenna with smaller dishes or work with other radio observatories. During Voyager 2's encounters with Uranus and Neptune, NASA used antenna arrays to handle the increasing distance and return more data. Voyager helped shape the deep space network itself. When the probes were launched, the network already had decades of experience supporting lunar and planetary missions, but the Voyager encounters demanded greater sensitivity. The 3 largest antennas were originally 64 meters across. Between 1982 and 1988, they were expanded to 70 meters, partly to prepare for Voyager 2's distant flyby of Neptune in 1989. Expanding a radio dish is not quite as simple as adding a wider rim to a dinner plate. The structure must support the extra surface while preserving its shape and balance. Motors, bearings, control systems, and receivers may require modification. The antenna must remain capable of moving accurately despite the added size and weight. The upgrades represented major engineering projects, all undertaken because a spacecraft was moving so far away that Earth needed larger ears. Other parts of the system also improved. Receivers became more sensitive. Coding and data processing methods advanced. Computers became faster and could search for weaker signals. Arraying techniques were refined. Voyager's hardware remained largely unchanged, but the network listening to it developed around the mission. This is an important reason contact has lasted so long. Voyager does not have a 2026 radio system hidden inside its 1970s structure. Its transmitter, antenna, and onboard computers belong to the period in which it was built. The improvement occurred mainly on Earth. Each generation of ground equipment became better at extracting useful information from the same weak spacecraft transmission. The Deep Space Network performs several jobs during a Voyager tracking session. Receiving telemetry is the most familiar. The spacecraft places engineering and scientific data onto its radio carrier, and the network reconstructs the digital bits. Those bits eventually become temperatures, voltages, instrument readings, particle counts, magnetic field measurements, and information about Voyager's operating state. Sending commands is another job. Instructions prepared by the mission team at the Jet Propulsion Laboratory are delivered to the appropriate Deep Space Network station. Powerful ground transmitters place those command bits onto an uplink radio signal and direct it toward Voyager. The antenna used to transmit may look much like the one used to receive, but the equipment involved must handle far greater radio power. Earth has a major advantage on the uplink. It is not restricted to Voyager's fading electrical supply. Ground stations can use transmitters producing tens or hundreds of kilowatts, then focus that energy through a large dish. Even so, the signal spreads enormously before reaching the spacecraft. Voyager's 3.7-meter antenna captures only a tiny portion, and its receiver must identify the slow command stream within the surrounding noise. Not every antenna supports every frequency or every mission requirement. Some dishes are equipped for particular radio bands. Others may be undergoing maintenance supporting a different spacecraft, or positioned where Voyager is below the horizon. Mission planners must match each communication need with an available antenna that has the correct equipment and geometry. Tracking is the network's third major responsibility. The same radio link used for communication can reveal how Voyager is moving. When the spacecraft receives a stable signal from Earth and returns a related carrier, engineers can measure the Doppler shift with great precision. That shift reveals the component of Voyager's velocity along the line between the spacecraft and the receiving station. Ranging measurements help estimate distance. Carefully designed tones or codes are transmitted to the spacecraft and returned. By measuring the total travel time and accounting for known delays in the equipment, navigators calculate how far away the spacecraft is. These observations are combined with models of gravity, orbital motion, solar radiation, and spacecraft activity to refine Voyager's predicted trajectory. Tracking does not mean the network watches Voyager visually. The spacecraft is far too faint and small to appear as a useful image. Its radio transmission becomes its marker. Small frequency changes show motion, and travel time shows distance. From these measurements, navigation teams can determine where the spacecraft should be, allowing the next antenna to point accurately enough to hear it again. The network also monitors itself. Every tracking pass produces information about antenna position, transmitter power, receiver performance, weather conditions, timing, and the health of numerous electronic systems. If a signal appears weaker than expected, engineers must decide whether the cause lies aboard Voyager, in the receiving equipment, in the atmosphere, or in the geometry of the pass. A problem may be as ordinary as a failed electronic component, or as inconvenient as heavy rain. Radio frequencies used for deep space communication can pass through clouds, but atmospheric water and other conditions may still affect signal quality, especially at higher frequencies. The antenna's elevation matters too. When Voyager is low above the horizon, its signal crosses more atmosphere and may encounter more local interference than when the spacecraft is high in the sky. The sun can create a more serious obstacle. At certain times, Earth and Voyager are positioned so that the line of communication passes close to the sun in our sky. The sun is an intense radio source, and its activity can overwhelm or distort the much weaker spacecraft signal. During these periods, known as solar conjunctions, communication may be reduced or temporarily paused. Commands are prepared in advance, allowing the spacecraft to continue operating while the radio path becomes unreliable. Ordinary tracking days require careful scheduling, even without the sun interfering. The Deep Space Network supports dozens of missions. Mars orbiters send large amounts of data. Lunar spacecraft need tracking. Probes near asteroids, Jupiter, and the Sun require commands and telemetry. New missions may need intense coverage after launch or during a critical maneuver. There are only so many antennas and hours in a day. A dish assigned to Voyager cannot simultaneously point toward Mars unless the two spacecraft happen to appear extremely close together and the communication setup permits shared support, which is uncommon. Schedulers must balance scientific priorities, emergencies, spacecraft visibility, antenna capabilities, maintenance, and the needs of international partners. Voyager does not receive continuous attention simply because it is the most distant spacecraft. Its data rate is low, and many of its activities are routine. The network listens during scheduled passes, often several times each week, depending on mission needs and antenna availability. Between those passes, Voyager may continue transmitting while no suitable dish is collecting the signal. That can feel wasteful until you remember how radio communication works. Voyager cannot easily store large amounts of data for long periods. Its memory is extremely limited by modern standards. Continuous low-rate transmission is often simpler than trying to save everything and wait for Earth to listen. The spacecraft sends its stream outward, and the Deep Space Network gathers it during the times assigned. When Voyager experiences a fault, the schedule can change. Extra antenna passes may be requested so engineers can collect more information or send recovery commands. This must be coordinated with other missions, some of which may also be approaching important events. A problem on a spacecraft 25 billion kilometers away can therefore rearrange work at facilities across 3 continents. During the effort to restore usable data from Voyager 1 in 2024, 6 antennas at the Madrid complex were arrayed together for the first time. The combined system listened for a special readout from the spacecraft's flight data system. That transmission helped engineers examine Voyager's memory and identify where corrupted information was being produced. The use of 6 dishes illustrates how the network can adapt. Voyager's transmitter could not be replaced or strengthened, but Earth could gather more antennas, combine their recordings, and improve the chance of recovering the data. Instead of asking the old spacecraft to perform beyond its abilities, engineers changed the receiving arrangement around it. Once a signal has been collected and decoded at a complex, the information travels through terrestrial communication links to the Jet Propulsion Laboratory in Southern California. The Spaceflight Operations Facility at JPL acts as the central point through which Deep Space Network data flow. Mission operations teams receive telemetry, examine the health of their spacecraft, and prepare new instructions. The radio signal may have spent almost a day crossing interstellar space, but once it reaches Earth, modern networks can move the recovered data between continents in a fraction of a second. A measurement collected in Spain or Australia can quickly appear on screens in California. The slow part is no longer transportation across Earth. It is the unavoidable light time between Earth and Voyager. Accurate timing is essential throughout the process. The 3 complexes and JPL maintain carefully synchronized time references. Fractions of a second matter when calculating radio travel, Doppler shift, and spacecraft range. If station clocks disagreed, navigation results could become inaccurate and signals from multiple antennas might not combine correctly. The antennas also require precise knowledge of their own locations. Earth's surface moves slightly because of tides, tectonic motion, and changes in the planet's rotation. For ordinary navigation, these shifts are tiny. For deep space tracking, they can matter. Engineers use detailed geodetic measurements and Earth orientation data to convert the position of an antenna on a rotating, imperfect planet into an accurate line toward a distant spacecraft. Even the atmosphere can alter the apparent travel time of a radio wave. Water vapor and charged particles in the ionosphere affect radio propagation. Corrections are applied using weather measurements, models, and signals at different frequencies. The aim is not merely to know that Voyager is far away. The aim is to determine its position and motion as precisely as the equipment allows. All these systems operate behind the simple phrase, "NASA received a signal." The announcement may describe a few bytes of engineering data, but receiving them required a global sequence of calculations and machines. Navigators predicted the spacecraft's location, schedulers assigned an antenna, operators configured transmitters and receivers. The dish moved into position. Timing systems synchronized measurements. Low-noise electronics captured the carrier. Computers followed the Doppler shift, decoded the telemetry, corrected errors, and delivered the result to the Voyager team. Much of this work is automated, but people remain central to the system. Engineers maintain antenna structures exposed to decades of wind, heat, dust, rain, and mechanical stress. Technicians service transmitters and cryogenic receivers. Operators respond when equipment behaves unexpectedly. Network planners negotiate competing mission requirements. Software specialists update systems without disrupting spacecraft that depend on old communication formats. The deep space network must modernize while remaining compatible with the past. New spacecraft may use higher frequencies, faster data rates, and optical communication experiments. Voyager still expects the radio protocols and command structures it was designed to receive in 1977. Replacing everything with the newest technology would be useless if the old spacecraft could no longer understand it. The network therefore carries several eras of exploration at once. One antenna may support a modern mission returning enormous amounts of data, while another listens for Voyager's 160-bit per second stream. Equipment added for future lunar and Mars missions must operate beside systems capable of communicating with machines whose original designers worked with magnetic tape, paper diagrams, and computers far less powerful than a current calculator. The 70-meter antennas themselves have aged alongside Voyager. They require maintenance and occasional periods offline for major upgrades. Bearings wear, transmitters need replacement, and old electrical systems must be renewed. Taking one of these dishes out of service can affect missions throughout the solar system, so work is planned carefully and alternative antennas are prepared where possible. NASA has also been adding new 34-meter antennas to increase the network's total collecting area and manage growing demand. Several smaller dishes offer flexibility. They can support different spacecraft separately, or be arrayed when one extremely weak signal requires more sensitivity. A collection of antennas is also easier to expand gradually than a single dish, larger than anything engineers have yet built. Future missions may increasingly use laser communication, sending data through tightly focused beams of light rather than radio waves. Optical systems can carry far more information, but they require extremely precise pointing and can be blocked by clouds. Radio will remain important, and Voyager will never be converted into an optical communicator. It left Earth carrying the system it has, and the deep space network must continue meeting it in the radio frequencies it knows. There is something reassuringly practical about that relationship. Voyager sends the same kind of narrow, low-power signal it has used for decades. The network does not demand that the spacecraft become modern. It builds better receivers, larger arrays, improves software and more accurate models on Earth, then uses them to keep an old connection working. As one tracking pass ends, the dish slowly moves away from Voyager's position. Data collected during the session continue toward JPL, where engineers examine the spacecraft's condition. Another antenna may already be preparing for a later pass. The network is not a single ear permanently fixed on one point in space. It is a coordinated set of instruments that continually turn from one mission to another. Voyager's signal gives the network an especially difficult target because of its distance. But distance is only half of the communication link. Earth can build dishes 70 meters wide, cool receivers, combine antennas, and predict frequencies with extraordinary precision. None of that will help if Voyager sends its radio energy in the wrong direction. Keeping Voyager, one small dish aligned with Earth, begins with a distinction that feels unusual when you first think about it. The direction a spacecraft is travelling does not have to be the direction it's facing. An aircraft usually points its nose roughly along its path because it must move through air. A car points along the road because its wheels determine where it goes. Voyager is travelling through an almost empty region, where there is no air rushing over its body and no road beneath it. It can move away from the sun in one direction, while keeping its antenna pointed back toward Earth. Turning the spacecraft changes its orientation, but it does not significantly change the path it is already following. This orientation is called its attitude. Despite the name, Voyager is not becoming difficult after nearly 50 years in space, although it would have every right to be. Attitude simply describes how an object is rotated in 3 dimensions. Mission controllers need to know which part of the spacecraft is pointing upward, downward, sideways, toward the Sun, or toward Earth. More importantly, Voyager's own control system must be able to notice when that orientation changes and correct it before the radio connection becomes too weak. The high-gain antenna is fixed to the main body of Voyager. It cannot swing independently through a wide range like a satellite dish on a rooftop. To aim the dish, the spacecraft must turn as a whole. Its cameras and several instruments were originally mounted on a movable scan platform, allowing them to look in different directions during the planetary encounters, but the large communication antenna remained attached to the spacecraft's central structure. The centerline running through the dish and the main body is known as the Z-axis. Under normal operating conditions, the axis is kept pointed toward Earth. Voyager is described as a 3-axis stabilized spacecraft. This means it controls rotation around 3 separate directions, commonly called pitch, yaw, and roll. You can imagine pitch as tipping the antenna upward or downward. Yaw turns it left or right. Roll rotates the spacecraft around the line passing through the center of the dish, rather like slowly turning a steering wheel while keeping it pointed toward you. All 3 directions have to be controlled. Correct pitch and yaw place Earth near the center of the antenna beam. Correct roll keeps the rest of the spacecraft aligned with the celestial references and operating conditions its systems expect. A spacecraft could still point its dish toward Earth while being rotated incorrectly around that line, but its star tracker might lose its guide star, thermal conditions could change, and some instruments or sensors might no longer face the intended direction. Voyager determines its orientation using a combination of sensors, star references, gyroscopes, computer calculations, and small rocket thrusters. The system responsible is called the Attitude and Articulation Control Subsystem, usually shortened to AACS. It is one of Voyager's 3 onboard computer systems and was designed specifically to control orientation, perform maneuvers, maintain antenna pointing, and during the planetary mission position the movable instrument platform. The AACS does not contain a modern image recognition program capable of photographing the entire sky and comparing it with a digital star catalogue. Voyager was designed in the 1970s, when onboard computing power was extremely limited. Its method is narrower and more direct. It uses the Sun as one reference and a bright star as another. Together, these provide enough information to stabilize the spacecraft in 3 dimensions. Sun sensors are mounted so that they can look through an opening in the high-gain antenna dish. These electro-optical devices detect the direction of sunlight and generate signals showing whether the spacecraft has drifted away from its intended alignment. The attitude control computer interprets those signals and determines which thrusters should fire to turn the spacecraft back. The Sun reference mainly controls pitch and yaw. If the spacecraft tilts too far upward, downward, left, or right, the Sun appears to move away from its expected position in the sensor. That creates a pointing error. The control system responds by firing the appropriate small thruster or pair of thrusters until the error is reduced. You might reasonably ask how pointing toward the Sun helps Voyager point toward Earth. Earth is not located inside the Sun, despite how some Monday mornings may feel. It travels around the Sun once each year and can appear slightly to one side from Voyager's distant viewpoint. Mission controllers therefore send the spacecraft updated pointing information, and the Sun sensor can be electrically biased or deliberately offset, so that Voyager aims close to Earth rather than directly at the center of the Sun. Distance makes this easier than it sounds. From Voyager's location, Earth's entire orbit appears very small. Imagine standing far away from a roundabout. A car moving from one side to the other may travel a considerable distance, but from your distant viewpoint, its apparent movement is only a tiny angle. Voyager is now so far from the inner solar system that Earth never appears very far from the Sun in its sky. The antenna does not need to swing across a broad region each year. It makes small changes to follow Earth's position around a sun that looks increasingly like a very bright star. Those changes still matter. Voyager's downlink beam is narrow enough that poor pointing would weaken communication. Mission navigators calculate the relative positions of Earth, the Sun, and the spacecraft, then prepare updated values for the control system. The command takes more than 23 hours to arrive, but Earth's orbit is predictable. Engineers do not need to know where the planet is at the instant they press a button. They calculate where it will be when Voyager receives and uses the information. The Sun alone cannot fully define the spacecraft's orientation. It can help determine whether Voyager is tilted away from the correct line, but the spacecraft could still roll around that line like a wheel turning on an axle. To control that third direction, Voyager uses a star tracker. The guide star traditionally associated with the mission is Canopus, one of the brightest stars in Earth's night sky. Canopus is useful because it is bright, easy for a dedicated sensor to recognize, and positioned well away from the region in which the Sun and planets appear to move. Voyager's star tracker does not admire Canopus in the way a person might look at a clear winter sky. It measures light within a particular field of view and sends information to the control system. To acquire the star, Voyager can roll around its sun-pointed axis until the tracker detects the correct bright object. The measured brightness is sent to Earth, so engineers can confirm that the tracker is locked onto Canopus rather than another star wandering through the sensor's view. Once the correct reference has been found, the spacecraft can use it to maintain roll orientation. There are 2 star tracker units for redundancy, although only one is normally used at a time. Redundancy was essential to Voyager's design. A mission travelling too far for repairs cannot depend on every component working perfectly forever. Engineers included backup computers, sensors, transmitters, receivers, thruster branches, and other duplicated systems wherever mass, power, and cost allowed. Even during the early mission, these backups mattered. One of Voyager 1's Canopus trackers began showing degraded performance before the Saturn encounter. Engineers studied the behaviour, developed methods to work around it, and kept the backup available. The spacecraft was already teaching its operators an important lesson. An aging component does not always switch neatly from working to failed. It may behave strangely, lose sensitivity, or remain useful only under carefully controlled conditions. Gyroscopes provide another source of attitude information. Voyager's inertial reference equipment can measure rotational motion without continuously looking at the Sun or a star. This is especially helpful during maneuvers, when the spacecraft deliberately turns away from its normal celestial references. A gyro does not tell Voyager where Earth is by itself. Instead, it senses how quickly and in which direction the spacecraft is rotating, allowing the computer to estimate changes in orientation. Gyros are useful, but they are not perfect permanent references. Small errors accumulate. A tiny measurement bias can gradually produce an incorrect estimate of orientation, rather like walking with your eyes closed while relying on the number of steps you've taken. You may remain close to the intended path for a while, but eventually a fixed landmark becomes helpful. The Sun and Canopus provide those external landmarks, allowing Voyager to correct drift in its internal estimate. After the sensors identify a pointing error, something must physically rotate the spacecraft. Voyager has no reaction wheels of the type used by many modern spacecraft. Instead, it relies on small hydrazine thrusters mounted around its body. These are miniature rocket engines designed to produce gentle forces in carefully selected directions. Each attitude control thruster produces only about 3 ounces of thrust, roughly 0.85 newtons. On Earth, that force would not impress anyone attempting to move a car. In space, there is almost no friction to resist it. A small force applied for a short time changes the rotation of the spacecraft. Another carefully timed firing can stop that rotation when the correct orientation has been reached. The thrusters work by allowing liquid hydrazine propellant to pass through a catalyst, where it decomposes rapidly into hot gases. Those gases expand through a nozzle and rush outward. According to Newton's third law, the spacecraft receives a push in the opposite direction. No oxygen tank is required because the chemical decomposition does not depend on burning hydrazine with atmospheric oxygen. Several thrusters are arranged around Voyager, so the control system can create turning forces in different directions. To produce rotation rather than simply push the entire spacecraft sideways, the system can fire thrusters positioned away from the centre of mass. It may also fire opposing thrusters in combinations that create torque while minimising unwanted changes in the spacecraft's trajectory. Suppose Voyager begins to yaw slightly to the left, moving the antenna away from Earth. A thruster on one side can fire briefly and begin rotating the spacecraft back to the right. Once the dish approaches the desired direction, another firing stops the motion. Without that second correction, Voyager would continue rotating, because space provides almost no drag to slow it down. This can be difficult to picture, because objects on Earth usually stop when a pushing force ends. Friction removes their motion. Slide a book across a table and it soon comes to rest. Rotate a chair and the bearings, air and your shoes eventually slow it. Voyager receives no such convenient assistance. If a thruster starts rotation, the attitude control system must deliberately cancel it. The spacecraft is not constantly firing jets in a continuous struggle to remain steady. Engineers define an acceptable pointing range around the ideal direction. Voyager is allowed to drift slightly within that range. When the error reaches a set limit, the control system performs a correction. This approach saves propellant and reduces wear because there is no need to react to every tiny disturbance. The acceptable range is sometimes called a deadband. Inside it, the spacecraft is considered pointed well enough. Move outside it, and the thrusters are commanded to fire. A very narrow deadband provides more precise pointing but causes frequent corrections. A wider one reduces the number of firings but allows the radio beam to move farther from Earth. During the original planetary mission, precise orientation supported camera observations, instrument pointing, and high-rate communication. In the interstellar mission, the high-gain antenna remains the main concern. The cameras are off, the scan platform is no longer being used for a busy program of planetary observations, and only a small number of scientific instruments remain active. This gives engineers more freedom to relax certain pointing limits, in exchange for preserving aging hardware. Voyager does experience small disturbances even in interstellar space. Sunlight exerts a minute pressure, although it is now far weaker than it was near Earth. Heat radiated unevenly from the spacecraft can produce tiny forces. A slight leak or an imperfect thruster firing can change the attitude. Moving parts once created their own reactions. The spacecraft may also carry a small amount of rotational motion left by previous maneuvers. None of these effects usually produces a sudden dramatic spin. The problem is accumulation. A small push that would be unnoticeable over a minute can become significant over hours or days. The control system watches the references and corrects the resulting drift before the antenna moves too far away. Because Voyager's radio signal is already extraordinarily weak, pointing accuracy and radio sensitivity are connected. If the antenna moves toward the edge of the acceptable range, less energy may reach Earth. Some data bits can become harder to decode. The deep space network may still detect the carrier, especially with a 70-meter dish or an array of antennas, but the margin between a readable signal and noise becomes smaller. Engineers must therefore balance two limited resources. One is radio strength. The antenna should remain closely aimed at Earth to maximize the received signal. The other is thruster life. Every correction uses a small amount of propellant and sends hydrazine through narrow passages that have been operating for decades. Voyager still has hydrazine, but merely having fuel in the tank does not guarantee that the thrusters can use it. Propellant travels through external fuel lines and then through much narrower inlet tubes inside each thruster. Every firing can leave an extremely small amount of residue. After tens of thousands of firings in almost half a century, that buildup has become significant. The internal inlet tubes are about 25 times narrower than the main fuel lines feeding them. A layer of residue that would seem trivial inside a wider pipe can restrict a very narrow passage. As the opening becomes smaller, the thruster may receive less propellant and produce less reliable force. Eventually, a tube could become blocked. Replacing it is impossible. Engineers cannot send a mechanic to remove the thruster, clean the inlet, and return it to service. Their only options are to change how Voyager uses the equipment, switch to another set, or attempt to revive hardware that was previously considered unusable. One response has been to widen the allowable pointing range. In 2023, the mission team adjusted the settings so Voyager could rotate almost 1 additional degree in each direction before firing its thrusters. The team also began favouring fewer, longer firings, rather than a larger number of short pulses. Each firing contributes some residue, so reducing the total number may slow the clogging process. Allowing more drift can occasionally weaken the communication link enough for a few data bits to be lost. It is a calculated compromise. Losing a small amount of information now is preferable to using the thrusters so frequently that the spacecraft later loses its ability to point altogether. The decision is similar to speaking slightly less clearly in order to preserve a telephone battery for a much longer conversation. Voyager also has more than one set of thrusters. Primary and backup attitude control branches were built into the spacecraft, while another group originally intended for trajectory correction maneuvers can perform some pointing duties. These trajectory thrusters helped adjust Voyager's path during the planetary flybys, when small changes were needed to reach Jupiter, Saturn and Titan at the correct positions. By the time the interstellar mission was well established, large trajectory corrections were no longer required. Voyager's path was essentially fixed, and the remaining thrusters could be considered for other tasks. Engineers revived the trajectory correction thrusters on Voyager 1 in 2017 and began using them for orientation control. Similar work followed for Voyager 2. These thrusters can help control pitch and yaw, but they cannot produce every required type of roll motion. Voyager still needs functioning roll thrusters to keep the star tracker aligned with its guide star. That made the condition of the roll control system particularly important. Voyager 1's primary roll thrusters had been considered unusable since 2004. Two small internal heaters lost power, and engineers concluded that operating the cold thrusters could be unsafe. The spacecraft switched to its backup roll thrusters, which continued working for about 2 decades. Under normal mission expectations, that would have been an excellent solution. The difficulty was that nobody in 2004 could be certain Voyager would still be operating in the mid-2020s. By 2025, residue buildup threatened the backup roll thrusters. The team began looking again at the primary set that had been abandoned 21 years earlier. Old telemetry, circuit diagrams, and spacecraft behaviour suggested a new possibility. Perhaps the heaters themselves had not permanently failed. An unexpected change in the electrical control circuits may simply have left them disconnected from power. Testing that possibility carried risk. If the primary thrusters fired while their heaters remained off, the cold propellant system could be damaged and might even experience a small explosion. The star tracker therefore had to be aligned as accurately as possible before the team attempted to restore heater power. If the tracker drifted too far during the procedure, Voyager's automatic programming might command the dormant thrusters to fire before engineers knew whether they were warm enough. Nothing could be watched in real time. Commands sent from Earth took more than 23 hours to arrive, and telemetry describing the result required the same journey back. By the time the team saw the response on their screens, the test had already succeeded or failed almost a day earlier. In March 2025, Voyager executed the command sequence. The returning telemetry showed the heater temperatures rising sharply, confirming that the circuits had been restored and the long-dormant thrusters could be warmed again. Equipment regarded as dead since 2004 had returned as a possible backup. The recovery did not make Voyager young, and it did not remove the residue from the thrusters currently in use. It gave the mission another option. When one system is approaching its limits, an old backup can become extremely valuable, even if that backup needs careful preparation before it can be trusted. This event also showed how antenna pointing depends on much more than the mechanical condition of a dish. The high-gain antenna has no major moving joint that must continually follow Earth. Instead, its direction depends on a complete chain of systems. Sun sensors must detect the correct reference. The star tracker must remain locked. Gyros must report rotational motion. The AACS computer must process those measurements. Electrical circuits must deliver power to valves and heaters. Hydrazine must pass through narrowing tubes. Thrusters must produce the expected force. The spacecraft structure must respond as predicted. A fault anywhere along that chain can threaten communication. In 2022, Voyager 1's AACS began returning impossible status information even though the antenna remained correctly pointed and the spacecraft continued operating. Engineers eventually found that the system had begun routing telemetry through a computer that had stopped working years earlier, corrupting the data before transmission. The strange reports created an uncomfortable situation. Ground controllers could hear Voyager and see that its radio signal remained stable, which suggested the antenna was still aimed at Earth. Yet the data describing the attitude control system made no sense. It was like driving a car that continued travelling normally while the dashboard insisted the wheels were inside the glove compartment. The team traced the incorrect routing, restored valid telemetry, and later prepared a software patch intended to prevent the problem from returning. Once again, the recovery depended on reasoning from delayed and incomplete information. Nobody could open the spacecraft or attach a diagnostic tool. Engineers examined the radio signal, compared impossible readings with the machine's actual behaviour, and tested explanations through commands separated by days of waiting. Voyager's own fault protection routines provide some defence when Earth cannot respond quickly. If the spacecraft detects certain problems, it can enter safer operating modes, change transmitter settings, or attempt to preserve its orientation. These routines were necessary even near the planets, but the long communication delay makes them essential now. Any serious pointing problem will develop long before mission controllers learn about it. The low-gain antenna offers a limited backup under some conditions. Unlike the high-gain dish, it spreads radio energy across a much broader region and does not require such precise pointing. That was useful near Earth early in the mission, when radio signals were strong enough to survive the lower concentration of energy. At Voyager's present distance, the low-gain link is far more difficult to use. The spacecraft's normal communication depends on the high-gain antenna remaining aligned. A complete loss of pointing could therefore become one of the hardest failures to recover from. If Voyager rotated far enough that the high-gain beam missed Earth, the deep space network might lose the downlink. Engineers could attempt to send commands into the broader reception pattern of the spacecraft's antenna system, but they would receive little or no immediate confirmation. The probe would need to recognize the command and restore its own orientation before anyone knew the effort had worked. The mission team tries to avoid reaching that condition by studying trends before they become emergencies. Thruster performance is measured over time. Engineers look at how long each firing lasts, how much rotation it produces, how frequently corrections occur, and whether temperatures remain within acceptable ranges. A small decline in effectiveness may provide years of warning if the data are understood correctly. Predictive maintenance sounds ordinary when applied to a factory machine that can be inspected every morning. On Voyager, the machine is more than 25 billion kilometers away. The information is almost a day old when it arrives, and the repair kit consists entirely of radio commands. Still, the principle is the same. Notice gradual changes, preserve alternatives, and avoid using a component more aggressively than necessary. There is no single point on Earth that Voyager's antenna follows. From the spacecraft's perspective, Earth is a planet moving around the Sun, while the deep space network antennas rotate with Earth's surface. Yet the difference between aiming at the planet's centre and aiming at California, Spain, or Australia is far too small to matter across this distance. The spacecraft points toward Earth as a whole. The ground stations take responsibility for placing themselves beneath the incoming beam. Even Earth itself would be invisible as a detailed world from Voyager's current position. The spacecraft's cameras are off, and they would not provide a useful image at this distance anyway. The attitude control system is not looking for blue oceans or white clouds. It follows mathematical pointing instructions and simple, dependable celestial references. That simplicity has helped it survive. A modern spacecraft might use sophisticated star catalogues, digital cameras, reaction wheels, and autonomous navigation software. Voyager relies on a bright sun, a bright star, gyros, small computers, and pulses of hydrazine. The design seems modest until you remember that it has maintained a communication link across the entire planetary system for almost half a century. Every successful transmission begins with this physical alignment. Before the transmitter places data onto an X-band carrier, before the deep space network collects the weakened signal, and before computers on Earth correct damaged bits, Voyager must hold its dish within the right part of the sky. The control system performs that work quietly, making small corrections that rarely receive attention unless something goes wrong. Electrical power is the quiet requirement behind everything Voyager 1 still manages to do. Its antenna cannot remain pointed toward Earth without powered sensors, computers, heaters, valves, and thrusters. Its scientific instruments cannot measure interstellar space without electricity. Its transmitter cannot send a radio signal, and its receiver cannot detect commands from Earth. Even the spacecraft's ability to notice that something has gone wrong depends on electrical circuits remaining awake. Take away the power, and Voyager does not merely become less capable. It becomes a silent object continuing along the same path, carrying working-looking equipment that can no longer operate. Near Earth, the most familiar way to power a spacecraft is with sunlight. Solar panels collect light and convert some of its energy into electricity. The International Space Station uses enormous arrays. Satellites in Earth orbit use smaller versions. Spacecraft visiting the inner planets can often rely on the Sun as well, although the details become difficult near places such as Venus, where heat becomes a serious concern. Voyager could not depend on that approach. Jupiter receives only about 1/25 as much sunlight per square meter as Earth. Saturn receives roughly 1/90. Continue outward to the distance Voyager occupies now, and sunlight becomes weaker still. Solar energy follows the same spreading rule that weakens a radio transmission. Double the distance from the Sun and the available light per square meter falls to about 1/4. Move 10 times farther away and it falls to around 1/100. Modern engineers have learned to operate large solar arrays as far out as Jupiter. NASA's Juno spacecraft does exactly that, although its 3 broad wings cover a considerable area and were designed with much newer solar cell technology. Voyager was built in the 1970s, when solar cells were less efficient, and its mission carried it beyond Jupiter to Saturn, before continuing outward indefinitely. A solar array large enough to meet its needs would have added mass, complexity, and awkward pointing requirements. By the time Voyager reached its present distance, even a very large array would receive extremely little light. The spacecraft therefore carries its own source of heat. Extending from one side of Voyager is a boom holding 3 cylindrical devices known as multi-100-watt radioisotope thermoelectric generators, or MHW-RTGs. The name is a little bulky, but each part tells us something useful. They generate electricity, they use a temperature difference, their heat comes from a radioactive isotope, and when they were new, each could provide more than 100 watts of electrical power. An RTG is often casually called a nuclear battery, which is reasonable as long as we do not imagine something resembling the battery inside a phone. It is not rechargeable, it does not store electricity through ordinary chemical reactions, and it cannot be plugged into a wall when its output declines. It is better understood as a long-lasting heat source attached to a solid-state electricity converter. Nor is it a small nuclear reactor. There is no controlled chain reaction inside Voyager. It has no control rods, circulating coolant pumps, steam turbine, or miniature engineer in a hard hat checking the pressure gauge. The heat appears through the natural radioactive decay of plutonium-238. Plutonium-238 is an unstable isotope. Its atomic nuclei gradually transform into other nuclei, releasing particles and energy in the process. Most of the radiation it produces is in the form of alpha particles. An alpha particle consists of 2 protons and 2 neutrons, the same basic combination found in the nucleus of a helium atom. Alpha radiation is not especially penetrating. A sheet of paper or the outer dead layer of human skin can block it when the source is outside the body. Inside an RTG, the alpha particles travel only a short distance before colliding with surrounding material. Their motion is converted into heat. The fuel remains warm continuously without burning, being stirred, or receiving any command from Earth. Voyager's fuel is not loose metallic plutonium, it is prepared as ceramic plutonium dioxide and contained within protective structures. The ceramic form is designed to resist breaking apart and spreading if an accident occurs. The heat source material is surrounded by layers intended to withstand the mechanical and thermal stresses of launch and possible re-entry incidents. That safety design mattered most in 1977, when each Voyager had to ride through Earth's atmosphere on top of a rocket. Once the spacecraft escaped, the RTGs became extremely dependable. There is no atmosphere around them to cause corrosion, no weather, and almost no chance of collision. The radioactive material simply continues decaying as the spacecraft travels. Heat alone, however, does not operate a computer. Voyager needs electricity, and this is where the thermoelectric part of the name becomes important. Each RTG contains many pairs of specially selected conducting materials joined together. These devices are called thermocouples. One side is kept hot by the plutonium heat source, while the other side faces outward and loses heat to space. A temperature difference across certain materials produces an electrical voltage. This phenomenon is known as the Seebeck effect. Push enough suitable thermocouples together in a carefully designed circuit, and the small voltages add up to provide a steady electrical current. There is no piston moving back and forth, no generator shaft turning, and no turbine spinning inside Voyager's RTGs. Electricity is produced directly from the difference between a hot inner region and a cooler outer region. That lack of moving parts is one of the system's greatest strengths. Mechanical machines can suffer from worn bearings, damaged lubricants, seals, gears, vibration, and fatigue. A thermoelectric converter can operate continuously as long as a useful temperature difference remains, and its materials continue conducting electricity. Voyager's RTGs use silicon-germanium thermoelectric elements capable of operating at high temperatures. Hundreds of these elements are arranged within each generator. The hot side receives energy from the decaying fuel. The outside of the generator includes fin-like surfaces that radiate unused heat into space. Only a relatively small portion of the thermal energy becomes electricity. Most of it leaves as heat, but efficiency was less important than durability. Voyager did not need the most economical generator ever built. It needed one that could work without maintenance for longer than anybody expected the spacecraft itself to survive. At launch, each of Voyager 1's 3 RTGs produced about 158 watts of electrical power. Together they supplied roughly 474 watts. That is less than many desktop computers now use under heavy load, and considerably less than an electric kettle, toaster, microwave oven or hairdryer. Yet it was enough to operate Voyager's computers, communications, instruments, heaters, and control systems. The comparison becomes even more impressive when you remember that Voyager did not carry one highly integrated modern computer. It carried several independent electronic systems designed with 1970s components. Instruments had their own electronics. The radio needed power. Heaters protected equipment from low temperatures. Motors moved the scientific scan platform. Tape recording equipment stored data. Cameras, spectrometers, particle detectors, and magnetic field instruments all had different demands. Mission planners created operational schedules to keep those demands within the available supply. During a planetary encounter, not every device needed to run at full power every second. Instruments could be turned on for observations and placed in standby when they were not required. Data could be recorded and transmitted later. Heaters could be managed according to temperature and activity. At first, power management meant organising a healthy electrical supply. There was enough electricity for the planned mission, along with a reasonable margin for unexpected conditions. Engineers still had to be careful, but they were not yet debating whether a few watts might determine the spacecraft's survival. That changed gradually because an RTG does not produce a fixed output forever. The plutonium-238 has a half-life of about 87.7 years. A half-life is the time required for half the atoms in a radioactive sample to decay. After one half-life, the material does not stop producing heat. Its output falls to about half the original level. After another half-life, it falls to about 1/4. Voyager has not yet travelled for a full plutonium-238 half-life, but nearly 50 years is long enough for a noticeable reduction in heat. There is also another source of decline. The thermoelectric materials themselves become less effective with age. Decades of high temperatures, radiation exposure, and changes within the materials reduce how efficiently they convert the remaining heat into electricity. The electrical output therefore falls faster than radioactive decay alone would suggest. At present, each Voyager loses about 4 watts of usable electrical power per year. 4 watts sounds harmless, until you place it inside a machine with only a little more than 200 watts left and almost no unnecessary equipment remaining. On Earth, 4 watts may be consumed by an indicator light, a router, or a device left plugged in overnight. We rarely notice it. Voyager's engineers notice every watt because the loss happens again the following year, and again the year after that. A system that fits within the power budget today may no longer fit several years from now. The decrease is predictable in broad terms. Engineers know the plutonium is decaying and the thermocouples are aging. They can model the long-term trend. What they cannot predict perfectly is how the rest of the spacecraft will behave as voltage margins shrink and temperatures change. Old components may draw slightly different currents. A heater may switch on for longer than expected. A maneuver can briefly increase power demand. A transmitter mode change can alter the load. Voyager's electrical system must keep its voltage within an acceptable range. If demand rises too high while the generators are unable to provide enough current, the voltage can fall. The spacecraft has fault protection routines intended to respond before the condition damages critical equipment. An undervoltage event can cause Voyager to shut down selected systems automatically. That sounds helpful, and it is. The difficulty is that automatic protection may not choose the arrangement engineers prefer for a long interstellar mission. It may interrupt scientific measurements, change operating modes, or create a configuration that takes days of delayed commands to understand and reverse. Mission controllers would rather reduce the load deliberately than allow the spacecraft to reach the point where it must protect itself. A reminder of that risk arrived during a routine roll maneuver on February 27, 2026. Voyager 1's power level dropped unexpectedly. The mission team knew that any additional reduction could activate the undervoltage fault protection. Because every command and response requires almost 2 days for the round trip, recovering from such an event would be slow and would carry its own dangers. The engineers responded by moving forward with a difficult decision already included in their long-term plan. On April 17, 2026, they sent commands to turn off Voyager 1's low-energy charged particles experiment. The instrument had operated almost continuously since 1977, measuring ions, electrons and cosmic rays from the solar system and galaxy. It had followed Voyager through the outer planets, the heliosphere, and into interstellar space. Switching it off saved power, but it also ended a scientific record lasting almost 49 years. This was not a case of an instrument failing naturally. The experiment was still capable of returning valuable data. It was sacrificed so the spacecraft's remaining systems could continue. One small motor associated with the instrument was left running because its spinning mechanism and operating history created additional engineering considerations. Spacecraft shutdowns are not always as simple as flipping one switch. Components may share power lines, affect temperature, provide mechanical stability, or interact with fault protection software. Engineers must examine not only what a device consumes, but what changes elsewhere when it stops. After that shutdown, Voyager 1 had 2 operating scientific instruments remaining. One is the plasma wave subsystem, which listens for electrical oscillations in the thin plasma surrounding the spacecraft. These waves can reveal the density and behavior of the interstellar medium. The other is the magnetometer, which measures the strength and direction of magnetic fields. Neither instrument requires a camera lens or a large moving platform. They can continue gathering useful information while Voyager travels through a region with no nearby planet to photograph. Their data rates are modest, which suits the weakening radio connection. Most importantly, they provide measurements that cannot be collected from Earth, because no other operating spacecraft is as far out in Voyager 1's direction. The decision to preserve those 2 instruments was made years in advance. The Voyager science and engineering teams established an order in which systems would be shut down as power declined. They considered scientific value, energy use, instrument health, thermal effects, and the uniqueness of each measurement. There is no perfect choice. Turning off an instrument saves electricity but reduces the mission's scientific return. Leaving every instrument on would preserve more data briefly, then risk losing the entire spacecraft sooner. Power management is therefore an attempt to exchange breadth for time. Voyager can do fewer things, but perhaps it can continue doing them longer. This process began decades ago. After the final planetary photographs were taken in 1990, Voyager's cameras were switched off. The wide-angle camera used about 16.8 watts, while the narrow-angle camera consumed about 18 watts. Their heaters and related electronics were also turned off over time. There was little nearby to photograph, so the scientific loss was limited, while the power savings were substantial. Other instruments ended their work as the mission changed. The infrared interferometer spectrometer had been useful for studying planetary atmospheres and temperatures, but it was not needed for interstellar particle measurements. The photopolarimeter and ultraviolet systems had fewer useful targets after the planetary encounters. Motors, heaters, scan platform equipment, backup supplies, and electronics were gradually removed from the electrical budget. The spacecraft became simpler year by year. At Jupiter, it behaved like a busy observatory, coordinating cameras and sensors during rapid flybys. In interstellar space, it acts more like a small monitoring station. It holds its antenna toward Earth, operates a limited set of detectors, checks its own health, and sends compact reports. Heaters have provided another major opportunity for saving power. Space is cold in the everyday sense, but a spacecraft's temperature is not determined only by the surrounding environment. Voyager produces internal heat through its electronics and RTGs. Sunlight, although weak now, contributes a little. Insulation slows the loss of heat, and different parts of the spacecraft can remain at very different temperatures. A heater uses electricity to protect equipment that might otherwise become too cold. Early in the mission, conservative temperature limits were based on testing, design requirements, and expected operating conditions. As power declined, engineers began turning heaters off and allowing components to operate below their original preferred ranges. That sounds reckless until we consider how cautious spacecraft specifications can be. An instrument may have been tested and officially qualified down to a certain temperature. That does not mean it will instantly fail 1 degree below the limit. It means engineers could guarantee its performance only within the tested range. Voyager has repeatedly continued working at temperatures colder than its original specifications. In 2012, a heater associated with Voyager 1's ultraviolet spectrometer was switched off, allowing the instrument to cool far below temperatures experienced during testing. It continued operating for years. Similar decisions saved energy across both spacecraft. Every heater shutdown is still a risk. Materials become more brittle when cold. Lubricants can thicken or freeze. Electrical properties change. Hydrazine propellant has a freezing point that mission controllers must avoid, especially in narrow fuel lines. A component may survive cold conditions for months and then fail without warning. The RTGs themselves provide considerable waste heat, but they are mounted away from the main body on a boom. This keeps their radiation and thermal effects from interfering too strongly with scientific instruments and electronics. It also means their warmth cannot simply be distributed wherever engineers need it. Voyager was not designed with a central heating system and adjustable radiators like a comfortable house. Heat reaches different components through conduction, radiation, and the activity of nearby electronics. Turning off an instrument can therefore save electrical power while making part of the spacecraft colder. Sometimes the reduced temperature causes a heater elsewhere to switch on, giving back part of the saving. In other cases, the cold threatens equipment more important than the instrument being removed. Mission planners use thermal models and telemetry to understand these interactions, but a spacecraft this old can still behave unexpectedly. Power also affects communication choices. Voyager carries both X-band and S-band radio equipment, along with primary and backup components. Different transmitter configurations consume different amounts of electricity. The high-gain antenna concentrates the signal, but generating the radio carrier still requires power. Reducing transmitter output would weaken a signal already close to the detection limit, so engineers prefer to save electricity elsewhere. The main transmitter must remain on during normal science operations because Voyager has little ability to store large quantities of data. If Earth is not listening, some transmissions pass unnoticed. The spacecraft cannot simply wait for a convenient moment and upload decades of measurements later. Continued science requires a working transmitter, a functioning data system, and sufficient power to keep the antenna aimed. The command receiver must also remain available. Turning it off would save electricity, but leave Voyager unable to hear Earth. In an emergency, engineers would have no way to change its configuration. For the mission to remain controllable, certain systems are not realistically optional. The attitude control computer, flight data system, and command computer must stay active. Sun sensors and star tracking equipment need power. Thruster valves and heaters must be available when pointing corrections occur. Temperatures and voltages must be monitored. The spacecraft has reached a stage where most remaining electrical loads support the basic ability to survive and communicate. This is why saving 4 or 5 watts becomes difficult. Earlier in the mission, engineers could shut down a camera, a heater, or an unused supply and gain a noticeable margin. Now, many obvious choices have already been made. Remaining systems are either scientifically valuable or essential to keeping Voyager alive. In 2023, the mission team adopted a new strategy that recovered a small amount of electrical power from a voltage regulation system. The spacecraft had been reserving energy to protect protect its instruments against possible voltage fluctuations. Engineers concluded that Voyager's electrical supply had remained sufficiently stable to reduce that reserve and redirect the power towards science instruments. The change gained several watts, enough to delay another shutdown. It also slightly reduced the protection available against irregular voltage. Once again, the team accepted a carefully measured risk, because the alternative was to stop an instrument sooner. This is how Voyager's extended mission continues, not through one miracle, but through a long sequence of small trades. A heater is disabled, a safety margin is reduced, a backup circuit is restored, a thruster deadband is widened, an instrument is retired. Each choice preserves some capability while giving up another. The RTGs make all of those choices possible because their decline is slow. A chemical battery might have been exhausted decades ago. Solar panels would now receive almost no useful energy. A mechanical generator would require motion and maintenance. The radioisotope systems provide steady direct current through day and night, near planets and between stars, without caring where the sun appears in the sky. They also operated continuously before launch. Plutonium does not wait for a countdown. Once the heat source material was prepared, it produced heat on Earth, during installation, beneath the rocket fairing, and throughout the mission. The generators could not be switched off to preserve fuel. Their decay proceeded at the same natural rate whether Voyager was photographing Jupiter or sitting quietly between tracking passes. That means the unused heat and lost electrical potential from the early mission cannot be recovered now. There is no reservoir containing the electricity Voyager did not need in 1978. RTGs produce power in the present moment. If the spacecraft uses less than the available supply, electrical regulation handles the excess. If it demands more, the voltage begins to fall. The system is reliable, but it cannot save today's output for use years later. The half-life also explains why the spacecraft will not suddenly run out of radioactive material. Plutonium-238 will continue producing heat long after Voyager stops communicating. Even centuries from now, the generators will remain warmer than their surroundings. The mission will end because the electrical output falls below what the spacecraft needs, not because the final plutonium atom disappears. As power declines, there may come a point when Voyager can no longer operate scientific instruments. Later, it may be unable to keep the transmitter and attitude control system active together. Engineers could attempt periods of reduced operation, alternate configurations, or other strategies, but Voyager's tiny memory and aging hardware limit what is practical. Eventually, the spacecraft may enter a condition from which Earth cannot recover it. The antenna could drift away, the transmitter could shut down, the command receiver might no longer have enough power. Fault protection could place the spacecraft in a mode that cannot be sustained. Even then, the RTGs would continue releasing heat. A small electrical current might remain, but not enough to organize the spacecraft systems into useful operation. Voyager would keep moving at the same speed, its large antenna still attached, its record still protected, and its plutonium still decaying quietly on the end of the boom. That future has not arrived yet. The power margin is extremely narrow, but Voyager 1 remains in contact. Its plasma wave instrument and magnetometer continue sending measurements from interstellar space. Its computers still prepare telemetry, its receiver still waits for commands, its thrusters still correct the antenna's direction. The 3 RTGs still turn a fraction of their internal heat into the electricity required to hold that entire chain together. There is an appealing simplicity to the source. Voyager survives because some atomic nuclei are unstable. They decay at a rate set by nuclear physics, releasing heat without concern for distance, darkness, schedules, budgets, or the age of the spacecraft around them. Thermoelectric materials sit between that heat and the cold of space, producing a voltage. From that voltage come radio messages, scientific discoveries, and the ability to repair a computer from more than 25 billion kilometers away. Yet the power system does not remove the delay created by that distance. A generator can keep the receiver awake, but it cannot make a command arrive faster than light. Once a command leaves Earth, there is nothing more the Voyager team can do to it. The instruction has been checked, encoded, scheduled, and transmitted through one of the Deep Space Network's giant antennas. Its radio wave is moving at the fastest speed nature allows, almost 300,000 kilometers every second, yet even that is no longer fast enough to make communication with Voyager one feel immediate. The message must cross more than 25 billion kilometers before it reaches the spacecraft, and in the middle of 2026, that journey takes more than 23 hours in one direction. Think about what can happen during that time. A command transmitted in the morning may still be travelling when the engineers who sent it leave work. It continues through the evening, through the night, and into the following day. People eat meals, travel home, sleep, return to their desks and begin other tasks while the same set of radio waves is still making its way across the distance. Voyager has not ignored the command, it has not even received it yet. This makes the phrase communicating with Voyager slightly misleading if we imagine anything like an ordinary conversation. There can be no exchange in which one person speaks, another listens, and a response arrives a few seconds later. There is no opportunity for an engineer to say, "Try that switch," watch the spacecraft react, and then add, "No, not that one." Each instruction is more like a carefully prepared package released into space, with nearly a full day separating the sending from the delivery. Even after Voyager receives the message, Earth still does not know what happened. The spacecraft must interpret the command, perform the requested operation, prepare telemetry describing the result, and transmit that information back. The reply then needs another 23 hours or more to reach the Deep Space Network. The complete question and answer cycle is already longer than 46 hours, even before engineers spend time studying the returned data. By November 18th, 2026, Voyager 1 will become the first human-made object to reach a distance of 1 light day from Earth. At that moment, light and radio waves will need exactly 24 hours to travel between the spacecraft and our planet in one direction. A simple round trip will therefore take 48 hours. Earth will send a command on Monday, Voyager will not receive it until Tuesday, and the earliest possible reply will not arrive until Wednesday. That date will mark a useful milestone rather than a physical border. Voyager will not pass through a wall or cross a line painted across interstellar space. Its instruments will not detect a special one-light-day atmosphere, and the spacecraft will not receive a notification suggesting that delivery times may now be longer. The number matters because it gives the human mind a clearer way to understand the distance. Voyager will be 1 full day away, not by aircraft, train, or rocket, but by light itself. The delay also changes slightly as Earth moves around the Sun. Voyager continues travelling outward, so the general trend is toward longer communication times. Earth, however, spends 6 months of each year moving a little closer to Voyager's direction, and 6 months moving a little farther away. The difference is small compared with the total distance, but it means the one-way light time does not increase at exactly the same rate every day. Mission planners account for that motion in their calculations. They do not simply assume every command takes a fixed number of hours. The Deep Space Network knows the expected distance between its antenna and Voyager at the time of transmission. That value determines when the radio wave should arrive, when a response might begin, and when Earth should listen for the result. To follow one message properly, imagine an engineer at the Jet Propulsion Laboratory preparing a request for Voyager to read a region of its computer memory. The purpose may be to investigate a fault, verify a stored instruction, or check whether a component has changed state. Before anything is transmitted, the team must decide exactly what information it needs and whether the spacecraft can provide it safely. The desired action is converted into commands understood by Voyager's computer system. These are not sentences written in ordinary English. Nobody sends, "Hello Voyager, could you please look at memory location 245 and let us know what you find?" The instruction is represented by digital codes defining the target system, the operation, the timing, and any required values. Specialists review those commands to confirm that they will not interfere with other spacecraft activities. They examine power use, communication schedules, computer states, instrument operations, and attitude control requirements. A command that appears simple may behave differently depending on which mode Voyager is already using. Turning on one circuit could cause another to switch off. Reading memory could interrupt normal data flow. Changing a software address could affect instructions stored elsewhere. The proposed sequence is tested using ground simulations. Engineers maintain models and hardware capable of reproducing parts of Voyager's behavior. These test systems are not perfect copies of every aging component, but they help reveal errors before a real command is sent. The team may run the sequence repeatedly, adjust its timing, and ask independent specialists to check the result. This caution would be sensible even if Voyager were sitting in the next room. At its present distance, caution becomes essential. A bad instruction cannot be cancelled after transmission. Once the radio wave leaves the antenna, it travels onward according to physics. There is no faster signal available to catch it, and say that the team has changed its mind. For almost a full day, Earth must live with the knowledge that the command is on its way. If someone discovers a mistake 10 minutes after transmission, the spacecraft will still receive the original instruction. Engineers may send a second command intended to correct it, but that correction travels at exactly the same speed and remains 10 minutes behind. Voyager will execute the first command before the second one arrives. The only protection against that situation is careful preparation and the spacecraft's own fault detection logic. Voyager can reject commands that fail certain checks. It can also respond to some dangerous conditions by switching modes or shutting down equipment. Yet those protections were designed decades ago and cannot anticipate every unusual combination the aging spacecraft may encounter. As the command crosses space, it passes through regions that once seemed unimaginably distant from Earth. Within little more than a second, it has travelled beyond the Moon's average orbit. After 8 minutes and 20 seconds, it has crossed the average distance from the Sun to Earth. Depending on the planet's positions, it passes the orbital scale of Mars within minutes, Jupiter in less than an hour, and Neptune within several hours. Then it continues. The outer planets do not mark the halfway point. They are all relatively close to the Sun compared with Voyager's current location. After the signal passes Neptune's orbit, it still has most of its journey ahead. It crosses the region filled by distant icy bodies, travels beyond the heliopause, and enters the interstellar environment through which Voyager is moving. Nothing visible accompanies the command. The radio wave does not illuminate dust or leave a glowing line through the darkness. It is simply a changing electromagnetic field, spreading outward in a narrow beam. The energy becomes weaker as the beam expands, but the message remains encoded within it. Meanwhile, Voyager continues moving. At roughly 17 kilometers per second relative to the Sun, the spacecraft travels about 1.5 million kilometers during the 24 hours in which a message approaches it. Mission controllers therefore aim not at the position where Voyager was when the command left Earth, but at the position where it is expected to be when the signal reaches that distance. This is similar to throwing a ball towards someone who is walking, except the person is more than 25 billion kilometers away. The ball takes almost a day to arrive, and missing would be rather inconvenient. Fortunately, Voyager's motion is steady and carefully tracked. The Deep Space Network's radio measurements allow navigators to predict its position with sufficient accuracy for the spacecraft to remain inside the transmitted beam. Voyager's receiving antenna collects a tiny portion of the uplink. The radio frequency equipment amplifies the signal and extracts the slowly arriving command bits. Earth sends those bits at only about 16 per second. That rate seems extraordinarily low beside modern communications, but slow transmission makes each bit easier for the old receiver to recognize. The spacecraft checks the command structure to decide whether it is valid. Synchronization patterns help the computer identify the beginning of the message. Address information directs it toward the correct onboard system. Verification bits reduce the chance that random noise will be mistaken for a legitimate instruction. Once accepted, the command may be executed immediately or stored for later. Voyager has an onboard clock and can follow timed sequences. During the planetary flybys, this ability was vital because important observations happened too quickly for Earth to control them directly. Even near Jupiter and Saturn, the light time delay made real-time operation impossible. The spacecraft had to carry out preloaded plans while its cameras and instruments moved from one target to another. The same principle continues now. Voyager can be told to perform an action at a selected spacecraft time. Engineers calculate when the command will arrive and how that local time relates to Earth's clocks. The spacecraft does not use modern internet time or receive daily updates from a global navigation system. Its internal timing equipment was designed in the 1970s, and mission controllers must account for its behavior and gradual drift. If the instruction requests a memory readout, the appropriate computer retrieves the stored values. If it changes a heater state, an electrical switch is activated. If it adjusts the attitude control system, Voyager may wait for a scheduled moment before firing a thruster. Some commands produce an immediate change in telemetry. Others may require hours or days before their effects become clear. The spacecraft then prepares a response. Its flight data system gathers measurements from engineering circuits and active scientific instruments. These values are placed into structured telemetry frames. Error-correcting information is added, and the data are passed to the radio system. Voyager's transmitter sends the reply toward Earth through the high-gain antenna. The outgoing signal begins another journey of more than 23 hours. By this point, the original engineers on Earth may have been waiting for more than a day, but they still know only that the command should have arrived. They do not yet know whether the spacecraft received it correctly, whether the computer executed it, or whether an unexpected problem occurred. This is the difficult interval in Voyager operations. A critical action may already have succeeded or failed, yet Earth remains unaware. The event exists in Voyager's recent past and Earth's informational future. During the 2025 effort to restore Voyager 1's long-unused roll thrusters, the mission team faced exactly this situation. Commands were sent to change electrical circuits, restart heaters, and prepare equipment that had been considered unusable since 2004. If the thrusters fired while still too cold, damage could occur. Once the sequence began, Earth could not watch the spacecraft in real time or intervene halfway through. When the telemetry finally arrived, engineers saw the recorded temperatures rise, showing that heater power had returned. The successful result was nearly a day old by the time the team celebrated it. Had the test failed, the failure would also have been nearly a day old before anyone knew. That delay creates a strange emotional experience for the people operating the mission. They may sit in a control room waiting for a signal, while understanding that the actual event has already happened. The spacecraft is not currently deciding whether to obey. It decided many hours ago. The radio waves carrying the answer are already somewhere between Voyager and Earth. There is no way to look through a telescope and learn the results sooner. Voyager is too distant and faint to observe in useful detail. Even if an impossibly powerful telescope could see the spacecraft, the image would still be delayed by the same light travel time. Vision, radio communication, and every other method based on electromagnetic radiation are limited by light speed. Eventually, the returning signal reaches the region of the planets. It crosses Neptune's orbit, passes through the inner solar system, and approaches Earth. The Deep Space Network antenna is already pointed toward the location where Voyager appears in the sky. Receivers search around the expected frequency and account for Doppler shifts caused by the motion of both spacecraft and planet. The carrier emerges from the background noise, computers lock onto it, recover the data symbols, apply error correction, and rebuild telemetry frames. The information travels from the ground station to JPL, where it appears on screens in a form the mission team can interpret. Only now does the original question begin to receive an answer. Perhaps the requested memory values are correct. Perhaps a heater has warmed. Perhaps a fault flag has cleared. Perhaps the data reveals something nobody expected. Whatever the result, nearly 2 days may have passed since the first command left Earth. If another instruction is needed, the cycle begins again. Engineers analyze the response, discuss possible explanations, prepare a new sequence, test it, review it, reserve antenna time, and transmit. The next useful piece of information may arrive several days later. This slow rhythm became especially clear during Voyager 1's major computer problem, beginning in November 2023. The spacecraft continued sending a carrier signal, but the engineering and science data were unreadable. Mission controllers could tell that Voyager was still operating and receiving commands, yet they could not see its normal health information. Investigating the failure required a long series of experiments. The team sent instructions intended to make different computer systems respond in recognizable ways. Each attempt required roughly 22.5 hours to reach Voyager at the time, followed by the same delay for the result. A single test could consume nearly 2 days, and an unhelpful response meant returning to the beginning with a new idea. In March 2024, engineers commanded the flight data system to perform what they called a poke, an instruction intended to make the computer try different software sequences and reveal information about its condition. The resulting signal helped the team identify a complete readout of the system's memory. Analysis showed that one memory chip had failed. That chip held part of the software responsible for packaging data before transmission. The spacecraft was still making measurements, but the damaged code prevented those measurements from being organized into a readable form. The obvious solution would have been to replace the chip, which was slightly inconvenient because it was attached to a spacecraft beyond the heliopause. Engineers instead decided to move the missing code into other working memory locations. No single available space was large enough, so the program had to be divided into sections. References within the software also had to be changed. If one part of the code expected information at an old address, it needed to be redirected toward the new location. This was delicate work on a computer with very little memory, and no modern operating system to manage the process automatically. The team began with the code needed to package engineering data. They transmitted the rewritten section on April 18, 2024. Then they waited. The command travelled for about 22.5 hours. Voyager stored the new code and began using it, and the returned telemetry took another 22.5 hours to reach Earth. On April 20th, the team saw readable engineering information for the first time in 5 months. The fix had worked. Yet that success did not arrive as a quick response to a button press. It was the result of months of delayed experiments, followed by a final test that demanded another 2 days of silence. Later commands relocated the remaining software and restored data from the operating scientific instruments. Every step had to be completed without overrunning memory, breaking other functions, or using more power than the spacecraft could provide. The light time delay made each stage slower, but it also encouraged careful thinking. Engineers could not rely on rapid trial and error. They had to make each trial informative. The delay influences ordinary operations as well. When the Deep Space Network begins receiving a tracking pass, the data show what Voyager was doing almost a day earlier. The temperatures on a display are old temperatures. The electrical currents are old currents. The pointing information describes an orientation Voyager occupied before travelling another 1,000,000 kilometres. Mission controllers build a current estimate from those delayed measurements. They know what commands were sent and when those commands should have arrived. They know how the spacecraft usually behaves after each instruction. By combining the last confirmed telemetry with planned activities, they infer what Voyager is probably doing now. This is sometimes called operating beyond real time, although the phrase can be misunderstood. The mission still occurs in real time aboard the spacecraft. Voyager's computers react to their sensors without waiting for Earth. Its thrusters fire when local conditions require them. Its instruments record the surrounding environment as it exists around Voyager. What Earth receives is a delayed report of that reality. The delay does not slow events near the spacecraft, it slows our knowledge of them. Imagine that a voltage suddenly falls aboard Voyager at noon, according to its local clock. Fault protection may respond within seconds, switching off equipment or changing operating modes. Earth cannot know about the event until the telemetry reaches us more than 23 hours later. By then, the emergency response has already been active for almost a day. Engineers then need time to determine what happened. If they send a recovery command immediately, Voyager still waits another 23 hours before receiving it. A problem can therefore continue for 2 days or more before Earth's first deliberate response reaches the spacecraft. This is why onboard autonomy matters. Voyager is not intelligent in the modern sense, and its computers are not capable of inventing new repair plans. They do, however, contain rules for recognizing certain faults. If the spacecraft loses its celestial references, it can search for them. If power voltage falls too low, systems can be shut down. If a computer stops behaving correctly, backup equipment may take over. These automatic responses were written because delayed communication was always part of planetary exploration. At Saturn, Voyager was already more than an hour away by radio. A sudden problem during a close flyby could not wait for Earth to notice and reply. The spacecraft needed to protect itself long enough for the ground team to understand the situation. The present delay simply pushes that principle much further. Voyager must be trusted to remain safe through almost 2 days of uncertainty. Its rules are limited, but without them, the mission would have ended long ago. The light time also prevents continuous manual control of scientific observations. An engineer cannot point an instrument at a feature and adjust it while watching the results. There are no nearby features now, but even routine measurements must be scheduled and transmitted according to plans prepared in advance. Voyager's active instruments generally operate continuously or according to simple patterns. Their data are combined with engineering telemetry and sent at low speed. When scientists examine a plasma wave event or a change in magnetic field, they are studying something that occurred almost a day before the signal reached Earth. For many scientific questions, this delay causes no serious problem. Interstellar plasma conditions do not need to be observed live for the measurements to remain valuable. A magnetic field reading is still useful after 23 hours, just as information from an ancient star remains useful, even though its light has travelled for centuries. Operationally, however, the delay makes timing important. Engineers must distinguish between the time an event occurred on Voyager, the time its signal left the spacecraft, the time Earth received it, and the time analysts began examining it. Logs record these different moments carefully. Suppose telemetry received at 10 AM shows a thruster firing. That does not mean the firing occurred at 10 AM Earth time. It may have happened the previous morning. If the firing was triggered by a command, the command itself may have left Earth another day before that. A single action can therefore connect 3 different days. Earth sends the request on one day. Voyager performs it on the next. Earth learns the result on the day after that. This delayed structure becomes even more noticeable during weekends and holidays. A command can be transmitted before a team leaves for the evening, arrive at Voyager while most of the people involved are asleep, and return after another workday has begun. Deep Space Network operators and mission specialists still cover required activities, but the distance follows no office schedule. There is also no guarantee that a reply will be received at the earliest possible moment. The correct Deep Space Network antenna must be available, and Voyager must be visible from that station. Other spacecraft may need support, equipment may be undergoing maintenance, the mission may choose to wait for a scheduled tracking pass rather than demand immediate coverage. Consequently, practical response times can exceed the simple round-trip light time. The 46 or 48-hour figure is a minimum set by physics. Real troubleshooting includes planning, review, scheduling, transmission, spacecraft execution, reception, decoding, and analysis. One useful exchange can occupy several days. As Voyager moves farther away, the delay continues growing. The increase is gradual, amounting to several minutes over a year rather than hours overnight. Engineers adapt their schedules and software models accordingly. There will be no point when communication suddenly becomes impossible merely because the one-way time reaches 24 hours. Distance will eventually contribute to the end of contact by weakening the signal and making recovery from faults harder, but the duration itself is not the main limit. Earth could, in principle, exchange messages with Voyager at even greater delays as long as the spacecraft had power, maintained its antenna pointing, and transmitted a detectable signal. The waiting is inconvenient, but it does not damage information. A digital command remains the same whether it travels for 1 second or 1 day. Radio waves do not become confused because the journey is long. The challenge is keeping enough of the signal above the noise and making sure the aging equipment at both ends continues to operate. There is a useful lesson in the way Voyager's team works with this delay. Modern technology often encourages immediate reactions. We expect messages to arrive at once, pages to load in seconds, and devices to respond before we have fully decided what we want them to do. Voyager offers no such convenience. It requires engineers to think first, check carefully, send one deliberate instruction, and accept that the answer cannot be hurried. The pace is slow, but it has not prevented remarkable repairs. A corrupted computer system has been reorganized from billions of kilometers away. Thrusters considered unusable for 2 decades have been revived. Communication modes have been recovered after faults. Instruments have been protected through changes in power and temperature. None of those achievements depended on defeating the light speed limit. The team succeeded by designing procedures that worked within it. They prepared for silence, used each response to narrow the problem, and treated waiting as part of the engineering process rather than an interruption to it. By late 2026, the nearly 2-day round trip will become a full 2-day round trip. A command sent toward Voyager will spend 1 day crossing space. The answer will spend another day returning. During those 48 hours, the spacecraft will travel nearly 3 million kilometers farther from Earth. Yet the old computer aboard it will continue recognizing the same basic digital language it learned before launch. 16 command bits will arrive each second, entering memory systems far smaller than those found in an ordinary modern appliance. Carefully written sequences will tell switches, instruments, heaters, and thrusters what to do. That raises the next practical question. The radio wave can cross the distance, and the deep space network can collect the reply. But what exactly happens when those bits enter a computer built in the 1970s? When Voyager 1 receives a command after its almost day-long journey from Earth, the signal does not enter anything resembling a modern laptop. There is no touchscreen waiting to light up, no familiar operating system, and no cheerful notification announcing that a new update is ready to install. The radio bits are passed into a collection of specialized computers designed during the 1970s, when a computer powerful enough to fill a desk was impressive, and storing a photograph could require more equipment than most homes contained. These machines are slow, small, and extraordinarily limited by current standards, yet they have controlled Voyager across billions of kilometers through encounters with Jupiter and Saturn, beyond the heliosphere and into interstellar space. Calling Voyager's electronics one computer would be slightly inaccurate. Each spacecraft was built with 3 different types of onboard computer, and there are 2 of each type for redundancy. That gives Voyager 6 computer units in total, although the paired systems are not all performing identical work at the same moment. Each type has a specialized responsibility, and together they provide command control, data handling, timing, scientific coordination, antenna pointing, maneuvers, and protection against certain failures. The first is the Computer Command System, or CCS. This is the part that receives instructions from Earth and decides which spacecraft system should act upon them. The second is the Flight Data System, or FDS. It gathers engineering and scientific measurements, organises them into the correct format, and prepares them for storage or radio transmission. The third is the Attitude and Articulation Control Subsystem, or AACS, which controls Voyager's orientation, fires thrusters, follows celestial references, and keeps the high-gain antenna pointed toward Earth. You might think of them as 3 small departments working inside the same travelling office. The CC reads the incoming mail and distributes assignments. The FDS collects reports, arranges them into tidy packages, and sends them home. The ARCS keeps the entire office facing the correct direction, so the letterbox does not end up pointed toward a completely unhelpful part of the galaxy. None of these systems could replace all the others without major changes. The CCS understands commands and manages sequences, but it was not designed to process every scientific instrument reading. The FDS understands telemetry formats and instrument data, but it does not directly manage all attitude control decisions. The AACS knows how to interpret sun sensors, star references, gyroscope measurements, and pointing errors, but it does not decide which plasma wave data should be placed into the next transmission. This division of labour was a practical response to the technology available when Voyager was built. Creating one general-purpose computer powerful enough to manage the entire spacecraft would have been difficult, risky, and potentially wasteful. Specialised machines could be designed around limited sets of predictable tasks. Their hardware and software could be tested separately, and a problem in one area would not necessarily destroy every other capability. The total memory contained across all 6 computer units is only about 32,000 words, equivalent to roughly 68 kilobytes when expressed in a more familiar modern comparison. The exact relationship between a Voyager word and a modern byte depends on the system, because the computers do not all use the same word size. The CCS and AACS work with 18-bit words, while the FDS uses 16-bit words. A word is simply the amount of digital information a processor handles as one basic unit. Modern computers usually work with much larger word sizes and memory capacities, measured in billions or trillions of bytes. Voyager's designers counted individual words carefully because everyone represented valuable physical hardware. 68 kilobytes is less storage than many ordinary digital photographs. It is smaller than numerous documents, songs, web pages, and phone applications. A modern icon displayed on a screen may contain more information than Voyager's entire onboard computer memory. Even a particularly enthusiastic restaurant menu downloaded as a PDF can outweigh the electronic memory controlling humanity's most distant operating machine. This comparison is amusing, but it can also be misleading. Voyager does not need to display photographs, run several applications, play music, manage a wireless network, or remember thousands of messages. Its computers were built for a narrow collection of tasks, and they carry out those tasks without the enormous layers of software found in present-day devices. A modern phone devotes memory and processing power to graphics, security, background services, user accounts, language support, cameras, location systems, animations, and countless features Voyager has never needed. Voyager does not care whether its buttons have rounded corners. It does not need to recommend a stronger password. It has never once attempted to show an advertisement before allowing engineers to check the magnetic field. The spacecraft software is written in forms of assembly language. Assembly is much closer to the basic instructions understood by a processor than languages commonly used for modern applications. Instead of describing a broad intention and allowing several layers of software to work out the details, programmers specify small operations involving memory locations, registers, comparisons, jumps, and input or output signals. One instruction might move a value from a particular memory address. Another might compare 2 numbers. A third might branch to a different part of the program if a condition is true. Long sequences of these simple operations create useful behaviour, much as a complicated mechanical clock can be built from gears that individually perform very modest movements. Programming at this level gives engineers precise control, but it leaves little room for mistakes. A wrong memory address may cause the computer to read unrelated information. An incorrect jump can send execution into the wrong routine. A value that is one bit different from the intended code may represent an entirely different instruction. There is no protective modern operating system standing between Voyager's programs and its hardware. The software interacts closely with the physical electronics. That makes it compact and efficient, but also means engineers must understand exactly how memory, timing, electrical signals, and spacecraft subsystems are connected. The CCS uses plated wire memory, a type of non-volatile storage that retains its contents even if electrical power is interrupted. Thin wires and magnetic materials store information through magnetization. It was chosen partly because of its reliability and resistance to the radiation environment of space. Each of the two CCS units contains 4,096 words. About 2,800 of those words hold fixed routines, while roughly 1,290 are available for variable information such as scientific sequences and updated operating instructions. The fixed portion includes code for decoding commands, monitoring faults, communicating with the other computers, and carrying out essential spacecraft functions. The word fixed does not mean that nothing aboard Voyager can ever be changed. It means that a substantial part of the control logic was designed to remain dependable and protected. Other memory regions can receive new sequences, revised values, and software modifications sent from Earth. The limited variable memory creates an unusual style of mission planning. Engineers cannot upload enormous files containing every action Voyager might perform over the next several months. They have only about 1,500 available 18-bit words across the CCS memories for storing sequence instructions and antenna pointing information. That may sound generous if a sequence contains only a few repeated activities. It becomes restrictive when every event is different. A detailed planetary encounter involving camera movements, instrument changes, data recording, and timed observations consumes memory quickly. Voyager's original flybys required carefully compressed sequences in which every instruction had a purpose. The current interstellar mission is easier in one respect because many observations repeat. Voyager does not need to photograph a new moon every few minutes, or rotate a scan platform between rapidly changing targets. Its remaining instruments monitor interstellar conditions continuously, or perform regular calibrations. Engineers can therefore use cyclic sequences. A compact set of instructions tells the spacecraft to perform an activity, and repeat it at regular intervals. The computer does not need a separate copy of the same command for tomorrow, next week, and next month. It follows the loop until another instruction changes the pattern. This is similar to writing repeat every hour, rather than filling hundreds of pages with the same reminder. The saving is enormous when memory is measured in a few thousand words. Voyager's normal operating plan includes what NASA calls a baseline sequence. This contains the recurring instructions needed to gather and return basic scientific information. Antenna pointing information can also be stored far into the future, allowing the spacecraft to continue adjusting for Earth's changing position. Additional activities are added through overlay sequences or smaller mini-sequences. An overlay may modify routine operations for a defined period. A mini-sequence may perform one particular engineering test, instrument calibration, or recovery action. These additions are developed on Earth, checked and transmitted through the Deep Space Network. The spacecraft also holds a backup mission load. This is a set of instructions designed to preserve some useful operation if Voyager eventually loses the ability to receive new commands. It cannot solve every possible failure, but it can change activities as power declines, stop using equipment that can no longer be supported, and continue returning basic data for as long as the remaining systems allow. Preparing for the loss of command reception may seem pessimistic, but it is exactly the kind of planning that has allowed Voyager to survive. Engineers do not assume the connection will always work. They give the spacecraft a limited plan for continuing alone. The CCS also stores fault protection algorithms. These occupy roughly 10% of its memory and respond to specific dangerous conditions. If radio power disappears, command reception fails, attitude control reports a serious problem, or electrical voltage falls outside safe limits, the computer can trigger a pre-programmed response. These routines are not artificial intelligence. They do not investigate the situation creatively or design a repair. Each one recognizes a defined signal and follows an established path. If this happens, switch to that unit. If the transmitter stops producing expected power, try a backup. If commands have not been received for a certain period, change the operating configuration. The simplicity is deliberate. A fault routine must be predictable. Engineers need to know what Voyager will do during the nearly 2 days required for Earth to learn about the problem and send a response. A system that invents an unexpected solution might create more trouble than the original fault. Alongside the CCS sits the Flight Data System, the computer responsible for turning measurements into messages. Each of its 2 units contains 8,198 words of 16-bit memory. The FDS receives information from scientific instruments and engineering sensors, controls certain instrument functions, maintains spacecraft time, and creates the formatted data stream transmitted to Earth. Formatting is more important than it may sound. Voyager's instruments do not all produce the same type of output. A magnetometer may report field strength and direction. A particle detector may produce counts arranged by energy. A temperature sensor may return a voltage that must be interpreted as a physical temperature. The FDS gathers these values and places them into known positions within a telemetry frame. When the frame reaches Earth, ground software knows where to look. Certain bits represent the state of a switch. Others belong to an instrument reading. Some identify the frame, mark timing, or support error detection. Without that structure, the receive stream would be a long series of ones and zeros with no clear boundaries or labels. The FDS also performs compression and data rate management. During the planetary encounters, Voyager generated far more scientific information than it could transmit immediately. Cameras alone could produce images faster than the radio link could return them, especially as distance weakened the signal. The spacecraft carried a digital tape recorder to bridge that gap. Despite the name, this was not a small plastic cassette of the kind once used for music. It contained about 328 meters of magnetic tape divided into 8 tracks. Its total reusable capacity was approximately 536 million bits, enough for around 100 full-resolution Voyager television images. The tape moved through a belt-driven mechanism. Data could be recorded at high speed during a brief encounter, then played back more slowly after the spacecraft passed the target. This allowed Voyager to observe a moon or ring system at the correct moment, even when the deep space network was unavailable, or the communication link could not carry the full data rate live. The recorder was an actual mechanical device, with moving tape and a transport system that had to function in a vacuum for decades. Many tape machines on Earth from 1977 now sit in museums, cupboards, attics, or boxes whose owners are confidently planning to organise them one weekend. Voyager's recorder continued to support scientific work far beyond its original mission. It has also been used during the interstellar mission to capture higher rate information from the plasma wave subsystem. Certain plasma wave observations can be recorded and later returned at about 1.4 kilobits per second, faster than Voyager's normal real-time rate of 160 bits per second. The recorder's users become limited by electrical power and aging hardware, and long-term onboard instructions are prepared for the time when it can no longer be supported. At 160 bits per second, Voyager transmits 20 bytes each second before we account for coding and formatting. A short plain text sentence may contain roughly that much information. A full page of text could take several minutes. A modern photograph would take days, and a video would require a degree of patience normally associated with geological processes. The tiny rate is not a sign that the computers are doing nothing. It reflects the weakness of the radio link, the spacecraft's limited power, and the kind of data still being returned. Magnetic field values and plasma wave measurements can be represented compactly. Voyager does not need to send a glossy image of interstellar space, which would mostly appear dark and would be a rather expensive way to confirm that nothing large is directly in front of the camera. The command uplink is slower still, at 16 bits per second. That rate is sufficient because commands are compact. Engineers are not sending long files containing colourful interfaces. They transmit codes, memory values, timing information, and tightly arranged instruction sequences. 16 bits can represent 65,536 different patterns. The meaning of a pattern depends on where it appears and which system receives it. A small collection of bits may identify an operation, while another group gives the required value or address. A command sequence can still require hours to transmit if it contains many words. The Deep Space Network sends it slowly enough for Voyager's receiver to detect each bit reliably. Engineers then wait almost a day for the final instruction to reach the spacecraft and another day for confirmation. Voyager's processors themselves work at a pace that seems almost leisurely beside current electronics. The master clock operates at 4 MHz, while the central processor's clock is only about 250 kHz. A typical instruction takes around 80 microseconds, allowing roughly 8,000 instructions per second. 8,000 instructions may sound fast until it's compared with billions of operations in modern devices, yet speed only matters in relation to the task. Voyager does not need to redraw a screen 60 times per second or analyze a live camera image. The spacecraft's environment changes slowly. Temperatures, voltages, particle counts, and pointing errors can be checked at rates its processors can manage. A thruster correction does not require billions of calculations. The attitude system measures an error, compares it with an allowed range, selects a response, and activates a valve. The physical spacecraft then rotates gradually. There is plenty of time for a processor operating at 1970s speed to keep up. The computers are interrupt-driven. An interrupt is a signal that tells a processor to pause its current task and respond to something requiring attention. A command has arrived. A timer has reached a scheduled value. A subsystem reports a fault. An instrument has data ready. Instead of repeatedly checking every possible condition as quickly as it can, the processor performs routine work until an event demands a response. This makes efficient use of limited computing power. It is a little like working quietly at a desk while several colleagues have bells they can ring when they genuinely need you, although one hopes the Voyager computers experience fewer unnecessary meetings. The third computer type, the AACS, also uses 18-bit words and contains 4,096 words in each of its 2 units. It processes information from sun sensors, star trackers, and gyroscopes. It calculates pointing errors, commands thruster firings, controls maneuvers, and once positions the movable platform carrying Voyager's cameras and several other instruments. The AACS must coordinate closely with the CCS. Earth may send a high-level command asking for a change in spacecraft attitude. The CCS decodes that instruction and passes the necessary information to the AACS. The AACS handles the detailed control, monitoring the rotation, and stopping the maneuver at the correct orientation. Communication among the computers occurs through carefully defined electrical interfaces. A value passed from one unit to another must arrive with the expected timing and voltage. Voyager's systems cannot exchange information through a modern network protocol. Their connections are physical circuits created for this one spacecraft design. That closeness between hardware and software can produce unusual failures. In 2022, Voyager 1's AACS began sending meaningless status reports, even though it was still keeping the antenna pointed correctly. Engineers discovered that data were being routed through a computer known to have failed years earlier, corrupting the report before it reached Earth. The functioning attitude system was not confused about Voyager's orientation. The path used to describe its condition was wrong. Engineers corrected the routing, and later prepared a software patch intended to reduce the chance of the problem happening again. Uploading that patch was not like installing an update on a home computer. Voyager's available memory was extremely limited, and different regions had different purposes. The team had to choose a safe location, verify that the new code would not overwrite something essential, examine every address it referenced, and consider what would happen if the upload were interrupted. The command was divided into steps. First, the patch was placed in memory. Then Voyager was instructed to read back the location so engineers could confirm the correct values had arrived. Only after the long round-trip delay and careful analysis could the patch be activated. Radiation adds another difficulty. High-energy particles can strike electronic memory and change a stored bit. A 0 can become a 1, or a 1 can become a 0. Sometimes the effect is temporary and can be corrected by rewriting the correct value. In other cases, a physical memory component may be permanently damaged. Voyager 2 experienced a flipped memory bit in 2010, causing its flight data system to format scientific information incorrectly. Engineers compared the received data, identified the changed bit, and sent commands to reset it. Once the correct value was restored, normal data returned. Voyager 1's 2023 failure was more serious. A single chip holding part of the FDS memory stopped working. The damaged region included software used to package engineering and science telemetry. The computer was still operating, the radio was still transmitting, and instruments could still make measurements, but the FDS could no longer arrange those measurements into a readable stream. No remote command could repair the physical chip. The mission team had to work around it using the small amount of memory that remained elsewhere. The missing software section was too large to fit into any single available location, so engineers divided it into pieces and stored those pieces in several separate regions. Then they changed the code itself. Any instruction that referred to the old memory address had to be updated. The separated pieces still needed to behave as one program. Other software needed to know where the relocated routines now lived. This work would be delicate on a current computer with immediate feedback and extensive debugging tools. On Voyager, the machine is almost a day away. Its memory map was created in the 1970s, and the result of each change takes nearly 2 days to confirm. The team began with the portion that prepared engineering telemetry. On April 18th, 2024, they transmitted the revised code to its new location. Voyager received it roughly 22.5 hours later. After the software began running, the spacecraft transmitted a response, which required the same travel time back. On April 20th, readable engineering information appeared on Earth for the first time in 5 months. The recovery showed that an apparently permanent hardware failure did not necessarily have to end the mission. Engineers could not mend the broken chip, but they could persuade the remaining computer to avoid it. Further commands relocated the rest of the affected code and restored science data. The process became one of the most striking examples of remote computer repair ever attempted, not because the individual programming techniques were unknown, but because of the age, distance, delay, and severe memory limitations involved. Maintaining the software also depends on records kept on Earth. Original diagrams, code listings, operating manuals, test reports, and engineering notes help current teams understand why the computer behaves as it does. Some information exists on aging media, or in formats no longer widely used. Knowledge must be transferred from people who designed and operated the spacecraft to engineers who joined the mission decades later. The problem is not simply finding someone who understands programming. Modern software developers may be extremely skilled while having little experience with plated wire memory, interrupt logic, 18-bit processors, fixed spacecraft routines, or telemetry formats created before standard personal computers became common. Voyager specialists learn the spacecraft almost as historians learn an ancient language. They study surviving documents, compare them with observed behaviour, speak with experienced team members, and reconstruct the reasoning behind decisions made long ago. The difference is that this ancient language still controls working machinery. Many of Voyager's commands were defined decades ago. Their numerical codes, electrical pathways, and expected effects have not changed merely because Earth's computers became faster. A modern workstation at JPL may prepare and validate the instruction, but before transmission, it must be translated into the old form Voyager recognizes. This creates a bridge between very different generations of technology. Contemporary software calculates the spacecraft's position, schedules deep space network time, models power and temperature, and simulates possible repairs. At the far end of the radio link, a small 1970s processor receives 16 bits each second and follows assembly instructions stored in a few thousand words. The old system does not know that the equipment on Earth has changed. It does not care whether a command was prepared on magnetic tape, a mainframe terminal, or a modern workstation. The pattern arriving at its receiver is either valid or invalid. If it matches the expected structure, the CCS acts upon it. This compatibility has been preserved deliberately. Ground systems can be replaced, upgraded, and virtualized, but they must continue producing the signals and command formats Voyager understands. A communication network that became too modern to speak with the spacecraft would not be an improvement. Small memory can even be an advantage when diagnosing a problem. The entire software system is limited enough that engineers can, in principle, understand every instruction and address. There are no millions of background processes, third-party libraries, or hidden automatic updates. Voyager's code may be old and difficult, but it is finite. The disadvantage is that there is almost nowhere to place a new solution. Every patch requires finding unused or less essential memory. Adding one function may mean moving another. A modern programmer might solve a problem by installing a larger package. Voyager's team may have to recover a handful of words and rewrite the solution to fit. The computers also operate continuously. They have not received the sort of regular, complete shutdown a household device experiences. Turning Voyager off and restarting it would be dangerous because power, timing, memory, attitude, and communication must return in the correct order. Some memory survives power loss, while other states may not. An unexpected restart could leave the spacecraft unable to point or transmit. Engineers therefore prefer precise changes to dramatic resets. They read memory, alter selected values, switch between redundant units, and observe the results. When a reset is necessary, its consequences are studied in detail before the command is sent. Redundancy gives the team alternatives, but it is not unlimited. 2 computers of each type were installed so that a backup could take over after a failure. Over nearly 50 years, however, some backups have already been used, degraded, or affected by their own problems. A component labelled secondary in 1977 may now be the only practical option. Switching computers can also change stored information. The backup may contain an older sequence or need updated values before assuming control. Electrical interfaces that have not been exercised for years may behave differently. Mission controllers cannot treat redundancy like opening a new device still sealed in its box. Despite all these limits, Voyager's computers continue doing exactly what makes contact possible. The CCS listens for commands and protects the spacecraft. The AACS keeps the antenna directed toward Earth. The FDS collects measurements, attaches timing, arranges telemetry, and passes the result to the transmitter. Each system performs a modest set of operations at a modest speed, and together they maintain an interstellar mission. The tiny data rate does not make the returned information unimportant. A few bits can show whether a heater is on. A short sequence can reveal that a memory location has changed. A slow stream from the magnetometer can measure conditions no other active spacecraft is directly sampling. Information does not become more valuable merely because it is large. Sometimes a single bit tells engineers that a backup system accepted a command. One temperature value can show that a restored heater is warming. One repeated pattern can expose a failed memory chip. Voyager's computers were never designed to impress anyone with speed. They were designed to behave predictably, survive radiation, conserve power, and control hardware far beyond immediate human reach. Their greatest achievement is not that they can compete with modern devices, it is that they are still useful, after the world that built them has changed almost completely. A command now begins on computers whose designers may not have been born when Voyager launched. It is translated into a format created before home internet, transmitted through a network of modernized antennas, and received by processors operating with kilobytes of memory. The old spacecraft carries out the instruction and returns a reply to machines billions of times more capable than itself. That arrangement works because the people on Earth continue learning how to speak Voyager's language. They cannot replace its processor, install more memory, or attach a new storage drive. They can only understand the systems already there and use the surviving space with great care. Those old computers make remote repair possible, but they also define what repair can mean. Engineers cannot replace Voyager 1's failed parts, clean its fuel lines, reconnect a loose wire, or remove a memory chip and fit a new one. They cannot attach diagnostic equipment directly to the spacecraft or inspect it through a camera. Voyager is more than 25 billion kilometers away, moving farther from Earth every second, and no existing vehicle could catch it within a useful period of time. Even if a repair mission could somehow be launched at extraordinary speed, Voyager would probably lose electrical power long before the new spacecraft arrived. Every practical repair must therefore be performed through radio commands, using the hardware that has already been aboard the probe since 1977. This changes the meaning of the word repair. On Earth, fixing a machine often means restoring it to its original condition. A broken component is removed, the damaged part is replaced, and normal operation resumes. Voyager repairs usually work differently. Engineers identify which parts still function, then rearrange the spacecraft's activities so those surviving parts can perform the most important tasks. The broken hardware may remain exactly where it was, still broken, while software and electrical switches guide signals around it. It is less like replacing a damaged road and more like studying an old map until you find another route through the countryside. That alternative route may be narrow, slow, and originally intended for something else, but if it leads home, it becomes the new main road. The first sign of trouble often appears as a small change in telemetry. A temperature may rise, a voltage may fall, a counter may stop advancing. Thruster firings may begin lasting longer than expected. A data pattern may become repetitive or impossible. Engineers watch long-term trends because an individual number can be misleading, especially on a spacecraft whose sensors have aged and whose internal temperatures have moved far outside the conditions expected during its original mission. Voyager cannot describe a problem in ordinary language. It does not send a message saying that one memory chip has failed, or that residue is restricting a thruster inlet. It sends bits representing measurements and operating states. The mission team must interpret those bits, compare them with earlier behavior, and determine which explanation best fits the evidence. Sometimes even those bits are wrong. In 2022, Voyager 1 began returning strange information from its attitude control system. The spacecraft continued pointing its antenna correctly toward Earth, and its radio signal remained stable, but the telemetry describing the system's condition was impossible. Values appeared that did not match any genuine operating state. If the data had been taken literally, Voyager seemed to be functioning incorrectly while somehow continuing to behave normally. That contradiction became useful. A serious failure in the physical pointing system would probably have changed the radio signal. If the antenna had wandered away from Earth, the carrier would have weakened or vanished. Because communication remained steady, engineers suspected that the attitude control system was performing its job while the information describing it was being damaged somewhere along the route to the transmitter. The investigation eventually showed that the attitude control data were being sent through a computer that had stopped working years earlier. Nobody had commanded Voyager to use that path. Something aboard the spacecraft had caused the data to be routed incorrectly, although the exact original trigger was uncertain. Engineers restored the proper route through the functioning computer and recovered valid telemetry. This repair required no new physical component. The failed computer remained failed. Earth simply changed which path the information followed. That kind of diagnosis begins with a model of the spacecraft. Engineers need to understand how electrical power, software, switches, sensors, and computers are connected. If one value is wrong but a related value remains normal, the difference can eliminate possible causes. If a transmitter works but telemetry is unreadable, attention turns toward the systems preparing the data rather than the antenna or radio amplifier. The team uses spacecraft documentation created during design, construction, and testing. Some records contain circuit diagrams. Others describe software memory locations, command formats, expected voltages, thermal limits, and backup operating modes. Old test results show how equipment behaved before launch. Those documents are essential, but they cannot answer every question. Voyager has spent nearly half a century in space. Radiation has passed through its electronics. Materials have warmed, cooled, expanded, and contracted. Thousands of thruster firings have moved propellant through narrow passages. Electrical components may no longer behave exactly as they did during tests in the 1970s. Engineers therefore combine the old design information with current telemetry. The diagrams explain what should happen. The data reveal what appears to be happening now. The difference between the two often points toward the fault. Ground simulators provide another layer of protection. The Voyager team can prepare a command sequence and test its expected effects before transmission. Software models reproduce the relationships among onboard systems, while specialized test equipment can imitate parts of the spacecraft's computers and communications. No simulator can perfectly reproduce a component that has aged in interstellar space. It cannot know exactly how much resistance has changed in an old circuit, or whether a switch will move cleanly after remaining unused for decades. It can, however, reveal logical mistakes. It can show whether a memory address is wrong, whether two commands conflict, or whether a planned action may activate equipment in an unsafe order. This is particularly important because Voyager commands cannot be recalled. Once transmitted, they continue toward the spacecraft at light speed. A second message can follow, but it cannot overtake the first. If engineers discover an error after the command has left Earth, Voyager will receive the incorrect instruction before any correction can arrive. Reviews are therefore conducted slowly. Different specialists inspect the sequence from different viewpoints. A software engineer may check memory addresses. A power specialist examines electrical demand. A thermal engineer considers temperature changes. An attitude control specialist asks whether the antenna could drift. Mission managers consider whether the scientific benefit justifies the risk. The final command may contain only a small number of bits, but many hours of human work can stand behind it. After transmission, the team waits. At Voyager's present distance, the command needs more than 23 hours to arrive. The spacecraft then executes it, and the response requires another 23 hours to return. Engineers cannot watch the action as it happens. By the time they see the result, it occurred almost a day earlier. This waiting prevents quick trial and error. A technician repairing a computer on a desk can change one setting. observe the response and make another change a few seconds later. Voyager engineers may need 2 days to complete one test. If the answer is unclear, another carefully designed experiment begins, followed by another long silence. The 2023 and 2024 flight data problem became a clear demonstration of this slow investigation. On November 14, 2023, Voyager 1 stopped returning readable science and engineering data. The Deep Space Network could still detect the carrier signal, and the spacecraft continued responding to commands, so the mission had not completely lost contact. The probe was transmitting, but the content of the transmission had become a repeating and unusable pattern. The team narrowed the problem to the flight data subsystem, the computer responsible for collecting and packaging telemetry. Somewhere between the scientific instruments and the radio transmitter, meaningful data were being turned into nonsense. Initial commands produced only limited clues. Engineers asked the spacecraft to change modes and tried to determine whether different parts of the computer were still operating. Each experiment consumed days because of the light time delay. Progress was measured in small differences within an otherwise unreadable stream. In March 2024, the team sent a command, sometimes described as a poke. It instructed the flight data subsystem to try different software sequences in the hope that one of them would produce a recognizable change. The resulting transmission contained a complete readout of the computer's memory. That readout was not neatly labelled with an explanation of the fault. Engineers had to compare it with the memory layout they expected. They eventually identified a failed chip containing part of the flight data subsystem software. The missing code included instructions needed to package engineering and science measurements for transmission. The failed chip could not be repaired physically. It could not be removed, warmed, cleaned, or electrically probed. The team's only option was to make the computer operate without it. A small amount of working memory remained available elsewhere, but there was no single empty region large enough to contain all the missing software. Engineers divided the code into sections and placed those sections in different locations. They also had to revise every instruction that referred to the code's former address. Imagine that part of a recipe has disappeared from a book. You copy different lines into the margins of several unrelated pages. Then you must change every note that says, "Continue on page 42, so that it directs the reader through the new sequence of scattered instructions. Miss one reference, and the recipe may suddenly ask for a spacecraft voltage instead of flour." The first relocated section handled the packaging of engineering data. It was transmitted to Voyager on April 18, 2024. For the next 45 hours or so, the team could do nothing but wait for the command to arrive and the resulting telemetry to return. On April 20th, readable engineering information appeared for the first time in 5 months. Temperatures, voltages, operating modes, and other health measurements once again made sense. The successful repair confirmed that the general plan worked. Additional commands relocated the remaining affected software. Science data gradually returned, and by June 2024, the instruments operating at that time were again sending usable measurements. The spacecraft had not been restored to its original condition. One memory chip was still dead. Voyager simply learned, through new instructions from Earth, to use the surviving memory differently. This repair was remarkable, but it followed a pattern established throughout the mission. Voyager has repeatedly continued by placing old equipment into new roles. In 2017, engineers noticed that Voyager 1's usual attitude control thrusters were becoming less effective. The small jets needed longer firings to produce the required rotation, suggesting that their performance was declining. The mission team looked toward another set of thrusters that had been used for trajectory corrections during the planetary encounters. Those thrusters had not fired since 1980. They had been inactive for 37 years, longer than many machines on Earth remain in existence, never mind operational service. Engineers developed and tested commands to use them for attitude control. When the sequence reached Voyager, the old thrusters responded successfully. Equipment designed to adjust the spacecraft's path near Jupiter and Saturn became part of the system keeping its antenna pointed toward Earth in interstellar space. A related problem involved Voyager 1's roll thrusters. The original set had been considered unusable since 2004 after 2 internal heaters lost power. The backup roll thrusters took over and worked for another 2 decades. By 2025, however, residue buildup inside the backup thrusters' fuel passages threatened their future operation. The team returned to the equipment abandoned in 2004. Old records suggested that the heaters themselves might not be permanently broken. An unexpected electrical change may simply have disconnected them from power. Attempting to restore them carried risk. If the cold thrusters fired before their heaters were working, the propellant system could be damaged. Engineers had to align the star tracker carefully, change the electrical configuration, restart the heaters, and wait for the returning telemetry. In March 2025, the data showed that the heaters had warmed. Thrusters considered lost for 21 years were once again available as a backup. This kind of work depends on Voyager's redundancy. 2 computers, 2 transmitters, multiple receivers, alternative thruster sets, and duplicate sensors were included because the designers expected failures. They could not predict which parts would fail or how long the mission would last, but they understood that a spacecraft beyond physical reach needed options. Redundancy does not guarantee survival. A backup may experience the same aging as the primary system. It may have been inactive so long that nobody knows whether it will respond. Switching to it can require electrical changes that disturb other parts of the spacecraft. Yet each alternative gives engineers another possible route around a fault. Sometimes the repair involves changing the way a component is used rather than switching to another one. When thruster inlet tubes began narrowing because of residue, the team widened Voyager's attitude-control deadband. The spacecraft was allowed to drift slightly farther before firing a correction. It also began using fewer, longer thruster pulses instead of many short ones. The antenna pointing became a little less precise, which could cause occasional data loss, but the number of thruster firings decreased. The aim was to preserve the fuel passages for as long as possible. Power management produces similar compromises. A heater may be turned off to save electricity, even though the connected equipment will become colder. A safety reserve may be reduced to provide a few more watts for scientific instruments. One experiment may be shut down so 2 others can continue. The engineers are not repairing one permanent version of Voyager. They are continually creating a new operating balance from whatever remains available. The work is complicated by the spacecraft's limited telemetry. Voyager cannot send detailed diagnostic records comparable with those produced by modern computers. Its data rate is tiny, and many internal conditions are represented only by basic voltage readings, temperatures, counters, or status bits. A single status bit might show that a switch is on, but not explain why it turned on. A temperature sensor may reveal that a component is cold, but not distinguish between a failed heater, a broken wire, or an incorrect command. Engineers request additional memory readouts, compare related channels, and deliberately change one condition at a time to see what happens. This is scientific reasoning applied to repair. Form a possible explanation. Predict what the spacecraft should do if the explanation is correct. Send a safe test. Wait nearly 2 days. Compare the result with the prediction. Then form the next explanation. The approach is slow, but it prevents random experimentation. Every test is designed to reduce uncertainty, even when it does not solve the problem directly. People often describe these repairs as engineering miracles. They are certainly extraordinary, but the word miracle can hide the preparation involved. Voyager's recoveries depend on decades of documentation, carefully designed backup systems, preserved technical knowledge, improved ground computers, and teams willing to study details that might seem insignificant. A note written in 1974 can become important in 2026. A retired engineer may remember why a heater circuit was arranged in an unusual way. A modern software specialist may create a tool that compares thousands of memory locations in seconds. A deep space network scheduler may find extra antenna time for a critical test. The spacecraft survives through all of those contributions. Repair also requires knowing when not to act. An old component that behaves strangely may still be performing an essential function. Resetting it could remove the fault, or it could prevent the system from restarting. Switching to a backup sounds safe until engineers realize that the backup has not been powered for 40 years. Sometimes the best decision is to leave the spacecraft alone while more data are collected. A stable fault may be less dangerous than an uncertain recovery attempt. This patience is particularly important because Voyager cannot be returned to a factory mode. Its current configuration includes decades of changes, retired instruments, unusual thermal conditions, reduced power margins, and software workarounds. A reset intended to restore original settings might activate equipment that should remain off, or demand more electricity than the RTGs can supply. The mission team must treat the spacecraft as it exists now, not as it appeared in its launch manual. There will eventually be a failure that no radio command can bypass. Both copies of an essential computer may stop working. The transmitter may lose power. The attitude control system may be unable to keep the antenna pointed toward Earth. A fuel line could freeze or become fully blocked. The electrical supply may fall below the level required to run the command receiver and transmitter together. Engineers cannot know which limit will arrive first. They can only observe the trends and preserve alternatives. Until that moment, every fault becomes another puzzle conducted across interstellar space. Earth sends a few carefully selected bits. The old computer receives them. A relay changes position, a memory location is rewritten, or a heater begins warming. Nearly a day later, Voyager sends back the evidence. The repair is never performed by hands touching the spacecraft. It is performed through understanding how a circuit was designed, how software moves through memory, how a radio carrier changes, and how one surviving component can replace another. That is how Voyager 1 has continued for almost half a century. It was built with backups, but it has survived because people kept finding ways to use them. It was given software, but it remained useful because later engineers learned how to rewrite it. It was launched with a fixed amount of power and propellant, but careful choices stretched those supplies far beyond the original mission. The final signal from Voyager 1 may not arrive with any clear announcement. There may be no countdown, no planned farewell message, and no single moment when everyone immediately knows that the mission has ended. The spacecraft is too old, too distant, and too complex for such a tidy conclusion. Contact is more likely to narrow gradually, as one capability after another disappears, until Earth can no longer recover useful information from the faint radio energy reaching the deep space network. Science will probably end before communication itself. Voyager can continue sending basic engineering telemetry after its instruments have been turned off, provided the computers, transmitter, antenna pointing system, and power supply remain functional. Even later, the deep space network might detect an unmodulated carrier signal without being able to decode detailed data. Hearing the spacecraft and understanding it are not exactly the same thing. As of July 2026, Voyager 1 remains active and continues operating 2 scientific instruments. Its magnetometer measures the magnetic field surrounding the spacecraft. Its plasma wave subsystem detects electrical oscillations in the extremely thin interstellar plasma. These instruments return measurements from a region no other operating spacecraft has reached. The spacecraft carried 10 sets of scientific instruments when it left Earth. Some stopped functioning, others completed their planetary work and were turned off. Still more were deliberately retired to conserve electricity. On April 17, 2026, engineers switched off Voyager 1's low-energy charge particles experiment after an unexpected power decrease during a planned roll maneuver left the spacecraft dangerously close to activating its undervoltage protection. The shutdown was expected to provide roughly a year of additional power margin. That does not mean Voyager is guaranteed to operate for another full year without difficulty. The saved power improves the margin, but any old component can fail unexpectedly. A computer chip can stop working, a thruster can become blocked, a heater circuit can change state, or a transmitter can become unstable. The spacecraft's age introduces uncertainty that cannot be reduced to one clean date. NASA has said that the Voyagers may continue operating into the late 2020s. The exact duration depends on power, temperature, hardware condition, and the success of future energy-saving measures. The available electrical supply falls by about 4 watts each year, while the spacecraft also cools as fewer devices remain powered. 4 watts is a small loss in an ordinary home and an important loss aboard Voyager. Most unnecessary systems have already been switched off. Each new saving now requires a harder decision because the remaining loads are either scientifically useful or essential for communication and survival. The magnetometer could eventually be turned off. The plasma wave subsystem could follow. At that stage, Voyager might continue sending engineering telemetry describing temperatures, voltages, computer states, and antenna pointing. The mission would no longer be collecting new interstellar science, but the spacecraft itself would remain an engineering experiment. Keeping contact after science ends could still have value. Engineers could study the long-term behavior of RTGs, computers, radios, thrusters, and materials operating farther from the Sun than any other working machine. Radio tracking could continue refining Voyager's trajectory. The mission might also test how weak a signal the deep space network can recover. NASA's Voyager frequently asked questions state that engineering data could continue for several years after science collection ends, and that the spacecraft may remain within the receiving range of the deep space network until around 2036, depending on whether enough power remains to transmit. That date is not a prediction that Voyager will definitely speak until 2036. It describes a possible communication limit if the spacecraft survives electrically and mechanically. Power is likely to become the decisive problem long before distance alone prevents reception. Voyager's signal grows weaker as the spacecraft moves away, but Earth can compensate to some degree. Larger antennas can be used. Multiple dishes can be combined. Receivers and signal processing software can improve. Longer listening periods can gather more energy from a slow data stream. Nothing similar can replace missing electrical power aboard the spacecraft. If Voyager cannot operate its transmitter, there is no signal for Earth to amplify. If the attitude control system cannot point the high-gain antenna toward us, most of the radio energy will travel elsewhere. If the command receiver turns off, the mission team cannot change the spacecraft's configuration. The power decline is gradual, but the final failure may be sudden. Voyager might operate normally one day and enter a protective mode the next. A momentary voltage drop could shut down equipment. Fault protection might choose a configuration that no longer leaves enough power to recover. An aging switch could fail during a routine change. The mission team prepares for such possibilities by maintaining power margins and planning shutdowns in advance. Instruments are not left operating until the spacecraft collapses. They are removed in an order designed to preserve the greatest scientific value for as long as possible. The remaining 2 instruments are especially valuable because they examine different parts of the interstellar environment. The magnetometer detects changes in the magnetic field carried through the local interstellar medium. The plasma wave subsystem can determine electron density when suitable plasma oscillations occur. Together, they help describe the conditions beyond the heliopause. Turning one off will leave a less complete picture. Turning off both will end Voyager 1's active scientific exploration. Yet those choices may allow the communications and engineering systems to survive longer. Temperature complicates the calculation. Switching off an instrument saves electrical power, but the instrument and nearby parts of the spacecraft become colder. Some electronics continue operating below their official design limits, while other components may be vulnerable. Hydrazine is a particular concern. The propellant used by Voyager's attitude control thrusters can freeze if its temperature falls too low. If the fuel lines freeze, the spacecraft may lose its ability to correct its orientation. The high-gain antenna would gradually drift away from Earth, and contact could end even while the transmitter and computer still had some electrical power. Heaters protect critical areas, but heaters consume electricity. Engineers must choose where warmth matters most. Saving a watt by switching off a heater is useful only if the resulting cold does not disable a system required to keep the spacecraft alive. The radio transmitter creates its own demand. Voyager's weak signal requires only a few tens of watts at the source, but those watts represent a significant share of the remaining electrical budget. The transmitter cannot be reduced indefinitely without making the signal too weak for Earth to detect. A future operating plan could involve transmitting less often, using different power modes, or allowing the spacecraft to spend periods in a quieter configuration. Such strategies are difficult because Voyager has limited memory and was not designed for long hibernation cycles. Turning systems off and restarting them also creates risk. An old component that is working continuously may not return after a power interruption. Engineers generally prefer stable operation. Every electrical switch movement, computer reset and transmitter change introduces uncertainty. Voyager has survived partly because many systems have continued doing the same simple tasks for decades. Distance still adds pressure. Voyager 1 is moving away at about 3.5 astronomical units per year. On November 18, 2026, it is expected to become the first human-made object 1 light day from Earth, approximately 25.9 billion kilometers away. A command will require a full 24 hours to reach it, and the earliest possible response will arrive another 24 hours later. That delay makes each future recovery slower. If Voyager enters a fault mode, it may remain there for several days before Earth can understand the problem and send a useful response. A condition that consumes extra power could become irreversible during the waiting period. The signal will also continue weakening. Radio energy spreads with distance, and Voyager cannot increase its transmitter power to compensate. The Deep Space Network may use its 70-meter antennas more often, or combine several smaller dishes. Improved processing can search more deeply within the noise. Eventually, however, the signal-to-noise ratio will become too low for reliable data. Individual bits will become uncertain. Error-correcting codes will repair some damage, but not unlimited damage. The data rate might be lowered further, giving the receiver more time to identify each bit. That could preserve contact for a while, although Voyager's available communication modes are restricted by its old hardware. There may be several different final signals. The final scientific measurement could arrive while Voyager continues returning engineering data. Scientists may later identify one last magnetic field, value, or plasma wave observation as the end of the active interstellar record. The final readable telemetry frame could arrive after science has stopped. It might contain temperatures and voltages showing a spacecraft still functioning, but running out of power. A carrier signal could continue after the data become undecodable. The Deep Space Network might detect a narrow radio tone indicating that the transmitter remains on, even though the spacecraft's computer can no longer organize useful information. Then there may be a last carrier detection, a faint signal appearing in one tracking pass and absent in the next. Nobody may recognize it as final at first. When a scheduled pass produces no signal, engineers will check the ground equipment. They will confirm that the antenna was pointed correctly, the receiver used the expected frequency, and no weather or interference problem affected the observation. Another Deep Space Network complex may try. Several antennas may be combined. The team will account for Doppler uncertainty. If Voyager's transmitter frequency has drifted, receivers can search a wider range. They may look for an X-band carrier, an S-band signal, or another known spacecraft mode. Commands may be transmitted even without a detected response. The team could instruct Voyager to switch transmitters, change receivers, reset a computer, restore antenna pointing, or enter a lower power configuration. Each attempt would require at least 2 days before a result could possibly return. A silence lasting several days would not automatically end the mission. Voyager 1 has experienced communication problems before. Engineers have recovered readable data after months of confusion. They know that old hardware can behave unexpectedly, and they will not abandon the spacecraft because of one missed tracking pass. Weeks may pass while different explanations are tested. Perhaps the antenna drifted, perhaps a transmitter failed, perhaps the spacecraft entered a fault protection mode. Each possibility suggests a different command sequence. The mission may continue sending recovery instructions long after the last confirmed signal. A working receiver aboard Voyager might still hear Earth even if the downlink transmitter has failed. Commands could activate backup hardware or restore a lost configuration. At some point, repeated attempts would produce no evidence that Voyager could respond. NASA would then have to decide that the operational mission had ended. The exact date might be assigned to the final received signal, the final successful command, or the later decision to stop recovery attempts. Even that administrative ending would not be the end of Voyager's physical journey. The spacecraft will continue travelling through interstellar space at roughly 17 kilometers per second. Losing electricity will not make it stop. There is almost no material around it to create drag. The sun's gravity will continue slowing it slightly, but Voyager is moving fast enough to escape. Its RTGs will remain warm after useful electrical generation ends. Plutonium-238 will continue decaying for centuries. The thermocouples may still produce small voltages, but not enough to operate the complete spacecraft. The computers may hold stored patterns in non-volatile memory. The antenna may remain pointed approximately toward the place Earth once occupied, although small disturbances will eventually change the orientation. The golden record will remain attached to the side of the spacecraft beneath its protective cover. Voyager will pass through the inner region of the Oort cloud in roughly 300 years and may require about 30,000 years to travel beyond its distant outer region. In the year 40,272, it is expected to pass within about 1.7 light-years of a star known as AC plus 793888, also called Gliese 445. That is a relatively close passage by interstellar standards, but still much too distant for Voyager to enter the star's planetary system in any ordinary sense. By then, the spacecraft will have been silent for tens of thousands of years. Its fate will no longer depend on batteries, thrusters, engineers, or the deep space network. It will simply follow an orbit through the Milky Way. Earth will continue moving too. The sun will circle the center of the galaxy. Stars will shift their positions. Constellations will change shape. The deep space network antennas now listening to Voyager will not exist forever, although their records may remain. The scientific data already returned will outlast the operational mission. Voyager's images of Jupiter and Saturn, its discovery of active volcanoes on Io, its observations of Titan, its measurements of the heliosphere, and its detection of interstellar conditions are stored in archives on Earth. Future researchers may analyze those measurements with methods unavailable today. A signal does not lose its value merely because the transmitter later falls silent. Data collected once can continue producing discoveries when new questions are asked. Voyager's engineering history will remain valuable as well. The mission demonstrates how redundancy, simple computers, careful documentation, radioisotope power, and patient ground operations can support an exploration program lasting much longer than planned. Future interstellar probes may use far more advanced technology, but they will still face distance, communication delay, limited power, and the impossibility of ordinary repair. What Voyager teaches is not that machines can operate forever. It teaches that thoughtful design can preserve options. A backup thruster unused for decades can become essential. A failed memory chip can be bypassed. a few watts can be saved. A radio signal weaker than almost anything around us can still carry meaning if Earth knows how to listen. The last signal will matter because it closes an unusually long conversation. Voyager 1 began speaking to Earth in 1977, when it was still near the planet and the full journey lay ahead. Its transmissions accompanied the first close views of Jupiter and Saturn. They continued while the spacecraft climbed away from the planetary plane, overtook Pioneer 10, crossed the termination shock and entered interstellar space. People who were not alive at launch now operate the mission. Some original team members spent entire careers working with Voyager and then watched it continue after retirement. Generations of Deep Space Network equipment have been replaced, while the spacecraft's own transmitter remained the same. One day, Edition California, Spain or Australia may turn toward Voyager and find only background noise. Computers will search near the expected frequency. Engineers will widen the search and check the calculations. Another station will listen. Commands will be transmitted into the darkness. Perhaps the signal will return, as it has before. Eventually one's silence will remain, and when that happens, it will not mean the effort failed. Voyager completed its original mission at Jupiter and Saturn decades ago. Everything after that has been an extension. The pale blue dot, the heliosphere crossings, interstellar science, and years of engineering performed across a distance light requires almost a day to cross. For now, the conversation continues. Two instruments are still measuring the environment around the spacecraft. The RTGs still provide enough electricity. The antenna remains directed toward Earth. The ancient computers continue accepting commands and preparing their slow stream of data. Somewhere above the plane of the planets, Voyager sends a radio wave toward the region where it calculates Earth should be. The signal spreads and weakens for hour after hour. It crosses the outer solar system, reaches one of Earth's largest antennas, and becomes a sequence of numbers on a screen. By the time those numbers arrive, Voyager has already moved more than 1 million kilometers farther away, yet the connection is still intact. And now, dear listener, you're a little farther along in your own evening than when we began. We started beside Earth, with a spacecraft launched in 1977, and followed it past Jupiter, Saturn, and the edge of the heliosphere. We listened to its radio whisper, stood beneath the giant dishes of the Deep Space Network, examined the small thrusters keeping its antenna aimed home, and looked inside the old computers still carrying out instructions. Perhaps it is late where you are. Maybe the room has become quieter, and the clock has moved forward without receiving much attention. So, what time is it now in your part of the world? And how far has Voyager travelled while you have been listening? During an hour, the spacecraft moves more than 60,000 kilometres. The distance grows, but Earth continues listening. If you found this journey calming, interesting, or helpful as you settle towards sleep, I would be grateful if you gave the video a like, subscribed, and shared it with someone else who might enjoy a quiet visit to the edge of human exploration. Voyager 1 will not answer forever. No machine will. But its signal has already travelled for longer, and from farther away than anyone who built it had reason to expect. Right now, beyond every planet, it is still operating. Right now, the Deep Space Network is still capable of hearing it. And right now, the long conversation between one small spacecraft and the world that sent it has not ended. So, let the antennas keep listening. Let Voyager continue along its path, and allow your own thoughts to become less busy for a while. Earth will remain here beneath the turning sky, receiving whatever faint information still makes the journey home. Sleep well, fellow traveller, wherever you are listening from tonight.